Hello and welcome to Sleepy Science. I'm so glad you're here. What if tonight we let curiosity move at the speed of calm? What if empty space wasn't empty at all, but flickered with borrowed energy and even pushed plates together? What if steady acceleration felt warm, horizons whispered quanta, and mass itself was a gentle drag from an unseen field? What if particles were only ripples on deeper seas? Solids just organized vibration, and new things emerged when simple rules locked arms. We'll picture electrons pairing into quiet currents, edges carrying traffic while interiors stay still, braids becoming identity, and patterns freezing from nothing. We'll touch the brink where phases change, see infinities tamed into measurable shifts, and watch quasi-particles prove that ideas can be real enough to weigh. Before we begin, where are you listening from? And what time is it? Under quiet stars or in warm indoor light? If this gentle wander helps you rest, please like the video and tap subscribe. It helps more sleepy minds find their way here. Now take a slow breath, feel the bed hold you, and let's drift. Vacuum fluctuations. Borrowed energy with receipts. You expect nothing to be quiet. But here's the hook. If you could turn down the universe's volume to absolute silence, you would still hear a soft hiss that never goes away. A restless murmur baked into reality itself. And tonight, you and I are going to sit with that murmur long enough to understand why the emptiest vacuum refuses to be still, how energy can seem to appear and vanish without cheating the books, and why the cosmos keeps impeccable receipts for every whisper it borrows. Begin by picturing space not as black emptiness, but as a sea of invisible fields that fill all of existence. Fields for light, for electrons, for every particle you've ever heard of. And even when those fields are in their lowest possible energy, what physicists call the ground state, they aren't flat lines but jittery traces, like a heart monitor that never reaches zero, because in the quantum world, minimum does not mean motionless. It means no further you can drain without breaking the rules. So when you ask the vacuum to sit perfectly still, it fidgets in place, a microscopic tremble you can't switch off. The careful part is not to imagine little. Marbles popping in and out of nowhere, as if the universe were printing. Money. Most of those popular sketches oversell the picture. What actually fluctuates are the fields themselves, and those fluctuations show up as uncertainty in measurable quantities, such as the electric and magnetic components of the electromagnetic field. Tiny variations that average to zero over time, but never settle to zero at any single instant. And this is the key. On average, the vacuum pays back what it borrows, yet in the moment it always looks a bit busy, like a perfectly balanced account that still has transactions scrolling by. You might wonder whether this borrowing is just poetic language, and that's a healthy instinct. Quantum theory is precise, but our everyday words are not. Still, there are grounded reasons to speak this way, because the ground state of a field carries what's called zero-point energy, not an optional add-on, but a baseline that shows up in calculations and, more importantly for your trust, in experiments that notice tiny shifts, extra noise floors, and subtle pushes that wouldn't exist if nothing were truly nothing. And while we'll explore those specific phenomena separately later, you can already feel the logic. Remove all particles you can name, chill everything toward absolute zero, isolate, shield, and silence, and the vacuum keeps humming. To see why that hum is unavoidable, imagine measuring a field's strength in a region of space with perfect precision, while also measuring how fast it's changing. And you'll run into a basic quantum tension that forbids locking. Down both knobs at once, push, one towards certainty and the other wriggles. So the calmest possible state is a compromise where the field is never exactly pinned, a permanent ripple of almosts that forms the vacuum's texture. And that texture has consequences you can stack up. It sets a floor for the jitter in ultra-sensitive detectors. It modifies how atoms behave when isolated from the world. And it even affects what counts as empty inside advanced circuits researchers use to probe microwave light. This may reawaken a common doubt in you. If there's energy in empty space, why can't we dip a straw into the vacuum and draw off free power forever? And the honest answer will steady you. Because the vacuum's fluctuations are symmetric and indifferent. They jostle, but don't give you a persistent push in one direction. And whenever clever setups seem to extract a nudge, the bookkeeping still balances once you include the whole system, including boundaries, materials, and the modes of the fields you allowed or forbade. So every apparent gain has a corresponding give. A clearer way to respect the receipts is to think in terms of allowed vibrational patterns, the way a violin string only sings at certain notes set by its length and tension. And the electromagnetic field in a region of space likewise supports specific modes, each with a ground state wiggle you cannot remove. Change the boundaries and you change the menu of allowed wiggles. Shift the sum of their ground state energies, and the world responds in ways that careful instruments can register. Not because particles blinked in and out like fireflies, but because you reshaped which fluctuations fit. Bring your attention to scale, and you'll see why these effects hide. The energy in each mode's ground state is small, and there are many modes, and their pushes mostly cancel. So only when you design geometry or materials to tip the balance do you reveal a net outcome. And that's why vacuum fluctuations aren't Hollywood magic, but laboratory tunable features of fields that have been measured, mapped, and put to work as both a nuisance to reduce and a signal to exploit. Still, the phrase borrowed energy holds a poetic truth you can trust. In quantum physics, we often compute how processes unfold by summing over possibilities, paths, configurations, ways the fields could briefly deviate. So the vacuum is not an empty stage, but the whole lighting crew and backstage rigging, constantly adjusting in ways you don't see yet that shape the play you do. And when you ask whether that's real, remember that reality in physics earns its name by affecting outcomes we can predict and test, and vacuum fluctuations pass that test. If you're worried this means the universe is unstable, take a breath. The vacuum's ground state is the safest place the fields can settle given the rules. And the restless quality is a sign of those rules holding, not breaking. The same way the random dance of air molecules keeps pressure steady in a sealed jar. Perhaps the most mind-clearing way to end tonight is to shift from something from nothing to structure from rules. What feels like emptiness is actually the simplest arrangement the laws allow. And the jitter you can't turn off is the footprint of those laws being simultaneously strict and probabilistic, enforcing balance while permitting momentary sway. And as you lie back and let this sink in, notice how your idea of silence has widened. Silence is not the absence of sound, but the presence of a floor below which sound cannot go. And vacuum is not the absence of reality, but the baseline reality cannot cross. So when you next imagine the universe between the stars, imagine not a vacant void, but a disciplined stillness alive with lawful tremble. A quiet that keeps the books perfectly balanced and hands you, gently, the receipt. Casimir pressure. Forces from empty space. You wouldn't expect two perfectly plain metal plates, uncharged and minding their own business in a vacuum, to creep toward each other as if a hidden hand were pressing them together. Yet that is exactly what careful experiments find. A tiny but relentless nudge called Casimir pressure. And tonight, you'll see how a force can rise from the way emptiness is shaped. Begin by imagining two ultra-flat mirrors facing each other with a hair-thin gap in between. Not a single particle trapped inside. No light, no heat, no static electricity, just space itself. And here's the counterintuitive move. Space is not a blank canvas, but a stage that allows only certain notes to ring. And when you squeeze that stage into a narrow cavity, you change which notes fit, trimming the spectrum of allowed electromagnetic wiggles between the plates compared with the richer spectrum outside. So the outside has more ways to vibrate than the inside, and that imbalance shows up as a net push driving the plates together. It's tempting to picture little particles bouncing around, but you don't need that mental image. What matters is mode counting. Like the way a violin string admits discrete tones while open air carries almost anything. And the cavity between plates is a string tuned by geometry, material, and temperature. So when you alter those knobs, you alter the force, sometimes even flipping its sign under special conditions. This isn't armchair physics, but benchtop reality. The Dutch theorist Hendrik Casimir put the effect on paper in the late 1940s, and half a century later, precision setups finally pinned it down. First with a millimeter-scale torsion pendulum that measured the attraction between a metal-coated sphere and a plate. Then, with microcantilevers and atomic force microscopes, reading deflections smaller than a red blood cell is thick, and across these instruments, Researchers learned the hard way that if you want to see pressure from nothing, you must subtract everything that is definitely something, like stray electrostatic patches, dust, humidity, surface roughness, and tiny tilts that masquerade as forces. Once those interlopers are caged, the story becomes remarkably consistent. Bring the surfaces closer and the pressure ramps up steeply. Separate them and it fades fast, making this a force that matters in the intimate world of micro and nanotechnology, but not for door hinges or bridges. And its sensitivity to distance explains a practical headache called stiction, where movable parts in micro devices latch onto each other and refuse to let go. A design risk engineers must anticipate, model, and sometimes exploit. While the original idealized mirrors were perfect reflectors, real materials are not. And the modern theory, often called Lifshitz theory, brings in the optical properties of the metals or dielectrics across a wide range of frequencies, the actual temperature of the setup, and surface details down to nanometer textures, because those features decide which modes are allowed and how strongly they press. This richer view unlocked a more dramatic twist. Under the right combination of materials and a fluid in the gap, the pressure can turn repulsive, a gentle anti-glue that pushes surfaces apart. And although it's weaker and trickier to achieve than the basic attraction, it has been demonstrated and is tantalizing for lubricating future nanoscale machines without oil. Researchers have also begun to rotate the idea, literally, by pairing anisotropic materials whose electromagnetic response depends on direction, predicting and seeking a Casimir torque that tries to align their crystal axes, a whisper of a twist born not from friction, but from the vacuum's preference for certain alignments of allowed modes. And measuring such torques is a frontier that refines how we think about empty space influencing real orientation. Another subtlety is temperature. Warm the system, and you add low-frequency contributions that gently reshape the pressure at larger separations, while cooling toward absolute zero reduces those thermal notes and hands the melody back to quantum effects. So experiments that vary temperature provide independent checks on the theory and warn designers how a device might behave from a cryogenic lab to a room temperature factory. As you think about applications, resist the urge to see Casimir pressure as a free energy source. Its direction and magnitude are set by geometry and materials, and any clever cycle you propose must pay back what it takes. A lesson nature enforces like a strict auditor, but do notice how it can be harnessed. To calibrate ultra-sensitive instruments, to create non-contact springs or dampers at tiny scales, to hold parts softly without wires or glue, and to teach students that even the quietest gap between metals is alive with consequences. Skeptics sometimes ask whether the force is simply ordinary van der Waals attraction in disguise, and that's a fair question, because at very short distances the two descriptions blend. But the power of Casimir's framework is that it spans the crossover. What used to be a patchwork of near-contact chemistry and far field, radiation pressure becomes one continuous story of fluctuating fields tamed by boundaries, with material response building the bridge, and experiments across distances from tens of nanometers to micrometers confirm that continuity. Perhaps the deepest lesson you can carry away is methodological rather than mystical. When the details of your boundaries matter, the empty regions between them stop being neutral background and start acting like participants, and physics becomes the art of counting what you can't directly see but can force to reveal itself through careful geometry, thorough calibration, and relentless subtraction of confounders, the scientific equivalent of listening for a faint instrument by muting the rest of the orchestra. So we close gently, two plain plates, a tiny gap, and a force that cares about every scratch and shimmer of their surfaces. That's the Casimir effect, an invitation to treat emptiness as structure, and to design with the invisible as if it were a material of its own, because at small scales it is. And when you next look at a polished piece of metal or a wafer in a clean room, remember that the space above it is not empty of influence but stocked with possibilities. And by choosing shapes and substances wisely, you can make the quiet in-between push, pull, or even twist, turning silence itself into a tool. Unruh effect. Heat from constant acceleration. You think heat comes from friction, flames, or sunlight. So here's a hook that bends your intuition. If you keep accelerating hard enough through what everyone else calls empty space, You will feel warmth where they feel none, as if motion itself has kindled a glow only you can sense. And this is the Unruh effect's simple but startling claim. Constant acceleration changes what counts as nothing. So an accelerated observer finds a genuine thermal bath where an unaccelerated observer swears there are no particles at all. To enter this strange territory cleanly, picture yourself strapped to a rocket that fires with unwavering push in a perfectly dark, perfectly cold universe. And imagine carrying a tiny, idealized thermometer that can absorb and emit the faintest quanta of light. According to the standard quantum picture of fields, your thermometer will begin to click as though immersed in a warm fog whose temperature rises in direct proportion to how hard you accelerate. Not because the universe has suddenly produced stuff from nowhere, but because particles are not absolute objects like stones. They are the way certain observers read the ripples of fields. And when your state of motion changes in a very specific, never-relenting way, the field's ripples reorganize in your frame into a pattern that looks exactly thermal. What changes so profoundly when you accelerate is the structure of what you can causally access. Because constant acceleration builds a personal horizon behind you, a boundary beyond which events can never catch up to your world line no matter how long you wait. And quantum fields on the far side of that horizon are entangled with those on your side. So when your description must ignore the part you can never influence, what remains is not a neat, pure vacuum, but a mixed, noisy state with the statistical fingerprints of heat, a deep lesson that temperature can arise not only from chaotic motion of molecules but from information you are forced to discard by how you move. To make this concrete without math, theorists analyze an ideal Unruh detector. Basically, a tiny two-state system riding along your accelerating path and coupled gently to a field, and they show that, under steady acceleration, it clicks with the same pattern and balance of excitations and de-excitations you would expect if the detector were sitting still in a genuine hot gas of Quanta. Same spectrum, same detailed balance, same dependence of click rates on energy gap. So the warmth is not metaphorical, but operational, tied to readings of a device that, in principle, you could build. Now your skeptical side might ask why we haven't simply flown a lab on a railgun and measured this already, and the honest answer is scale. The temperature is incredibly small for everyday accelerations. Push as hard as gravity at Earth's surface, and you get a warmth so tiny that it makes the cosmic background look like a furnace by comparison. And even the wildest lab accelerations we routinely give to protons or electrons in machines or with ultra-intense lasers translate to fractions of a degree when described in the clean, ideal limit. So while researchers have proposed clever routes to tease out related signatures, such as looking for extra noise in accelerated electron beams, or crafting analog systems whose excitations mimic the math of acceleration, a clear, unambiguous textbook demonstration remains a frontier rather than a trophy. In this light, the Unruh effect is less a laboratory trick and more a clarifying lens on reality. It tells you that particle content depends on motion and on horizons, and that the vacuum is not a universal object, but an agreement you make with your state of motion about which field ripples count as real excitations. And with that lens, you can make sense of surprising parallels. Near the mouth of a black hole, a stationary observer also sits next to a horizon and detects a thermal glow related to the gravity's pull there, which hints at a family resemblance between acceleration-driven temperature and horizon-driven temperature, though the detailed stories and settings differ in ways we'll explore elsewhere. Crucially, the Unruh effect demands endless, uniform acceleration, not just a brief shove, because it is the steady, never-ceasing push that erects and maintains the horizon that your frame cannot see beyond. And when the acceleration wobbles or turns on and off, the clean thermal picture blurs into more complicated radiation patterns that are interesting in their own right, but do not carry the simple thermometer, reading you'd quote as a temperature. Engineers and experimentalists care about this not only for philosophical reasons, but because any sensor that rides an accelerated platform, think nanoscale probes in vibrating environments or electrons surfing extreme laser fields, must contend with the idea that the quiet background is not the same background once you accelerate through it. And even if the predicted warmth is tiny, the conceptual rule shapes how we interpret noise, design detection strategies, and separate true signals from motion-induced effects. Look a layer deeper, and you meet a unifying principle. Temperature can emerge when a system is cut off from part of its own information, and uniform acceleration is a beautifully clean way to enforce such a cut, carving spacetime into an accessible wedge and an inaccessible wedge, after which quantum entanglement does the rest, uplifting your local state from perfect vacuum to something thermal once you accept that you cannot gather the missing correlations across the horizon. This is not mysticism, but bookkeeping, and it reminds you that ignorance enforced by geometry has physical teeth. You might wonder what becomes of energy conservation in this story. If you feel heat, where does the energy come from? And the consistent answer is that your rocket pays the bill, because keeping you in uniform acceleration requires continuous work, and the energy you harvest as thermal clicks is drawn from the force that keeps you accelerating rather than minted by the vacuum free of charge. A nice piece of cosmic accounting that closes the loop. It is also worth separating this effect from other phenomena that sound related but live in different neighborhoods. There are moving mirror setups that create quanta by quickly changing boundary conditions, and there are materials whose changing properties pump energy into fields in ways that look thermal. Yet the Unruh warmth rests on a distinct foundation: the way quantum fields carve up into modes for a uniformly accelerated observer who has a horizon, yielding a steady thermal spectrum without needing a mirror or a material at all. And so we end gently where we began, with your intuition about heat enriched rather than overturned. Warmth can come from burners and sunlight, yes, but also from the geometry of your path through space-time, from how relentlessly you push, and thus from how much of the universe your frame must give up on ever seeing. And once you let that idea settle, acceleration stops being just a change of speed and becomes a way of slicing reality into seen and unseen, known and unknowable, where a soft temperature appears not as a trick, but as a signal that your motion has built a horizon, and the horizon has charged you a fee you can read as heat on your own thermometer. Hawking quanta. Horizons distill information. You expect a horizon to hide things, not to cook them into signals. So here's a different doorway into the black hole story. Stand far from a quiet, non-rotating black hole and imagine holding the most patient thermometer you could build, and you'd find a faint, steady warmth coming from the darkness itself. A glow not from falling matter or hot gas, but from the horizon's own quantum behavior. And the startling claim, now the standard view, is that the boundary that lets nothing escape also distills information into outgoing radiation in a way that feels thermal up close, yet cannot be entirely random in the long run if the universe keeps honest books. To learn what that means without hand-waving, start with fields rather than particles, and picture the fabric of space near the horizon as a restless medium whose tiny ripples are entangled across that boundary, like duets sung in perfect synchrony by partners on opposite sides of a wall. And when you stay outside, you cannot hear the partner who vanished in, so you must average over the missing half of the duet, and what reaches you is a solo that sounds precisely like heat. This is Hawking radiation in operational terms. Not sparks from a surface, but a statistical imprint created when you are forced by the horizon to forget part of the quantum correlations that were there all along. From your faraway perspective, the temperature is fixed by the black hole's gravity at the horizon. Stronger gravity, hotter glow. And because bigger black holes spread that gravity over a wider region, they are colder than small ones, which means a massive black hole is practically frigid while a tiny one would simmer, radiate powerfully and evaporate faster. A remarkable reversal of everyday intuition where larger things usually cool slower. This glow is not a perfect blackbody because the space-time around the hole is a filter that lets some frequencies pass more easily than others. So the spectrum is thermal, but combed by the curvature and any surrounding matter, and as the hole radiates it loses energy, shrinks and gets hotter. accelerating the process in a feedback loop that ends, in theory, with a final burst once the mass is extremely small. Though for black holes born from stars, the timescales are so long that no human-made instrument will see one wink out. Now, the moment you accept that a black hole can evaporate, a deep puzzle arrives. What happens to the information about everything that fell in? The patterns in the light, the arrangement of atoms, the quantum details that tell one book from another. Because if Hawking radiation were perfectly featureless, those details would be lost for good, and that would clash with the principle that quantum evolution preserves information, a principle tested countless times and foundational to how we do physics. This information paradox sharpened an entire field of thought, and over decades the rough sketch of an answer has taken shape. The early radiation really does look thermal to any local test, but subtle correlations build up across the entire stream of emitted quanta as evaporation proceeds, so that the combined state of the radiation plus the remaining hole stays pure and bookkeeping remains exact. And once roughly half the hole's original entropy has been radiated, the so-called page time, the later quanta are entangled more with the earlier radiation than with the interior, suggesting that the information is not destroyed, but gradually woven into the outgoing glow in ways you cannot see by sampling just a cupful. You do not have to wade into forbidding equations to appreciate the ideas behind this recovery. One is soft hair, the notion that horizons can carry extremely delicate imprints of what fell in, encoded in long wavelength degrees of freedom that, in principle, can influence how radiation comes off. Another is the discovery, through modern gravitational path integrals, that when you try to compute the fine-grained entropy of the radiation carefully, new spacetime saddles contribute, often nicknamed islands, that effectively say part of the black holes inside should be counted as belonging to the radiation's description, and with those contributions, the entropy of the radiation rises at first, and then falls, tracing the hoped-for page curve consistent with information conservation. None of this implies that an astronaut falling through a large black hole would hit a wall of fire, an idea proposed to resolve the paradox but widely debated because, from the infaller's calm viewpoint, nothing special should happen at the horizon of a huge hole. And much of the current research balances that expectation against the outside observer's need for unitarity, finding ways that both can be true, depending on which questions you ask and which region of space-time you insist on describing. While we wait for a decisive observational handle, laboratory analogues offer a taste of the basic mechanism in cleverly engineered fluids, optical fibers, and ultra-cold gases. Researchers create horizons for sound or light, places where waves cannot escape, and then watch as quantum fluctuations near those horizons produce pairs of excitations with a thermal spectrum, a close cousin to Hawking's prediction that strengthens our trust that horizons and entanglement can conspire to make genuine radiation. Astrophysically, Hawking quanta from stellar or supermassive black holes are far too faint to see directly, drowned by the much brighter mess of hot plasma swirling around them. But exotic possibilities remain on the table. If the early universe forged tiny primordial black holes, their late-stage evaporation could contribute to high-energy signals, and constraints on such signals already teach us about what the cosmos did or did not produce. As your understanding deepens, the language of horizons distilling information becomes more than a metaphor. The horizon sets which correlations you are allowed to keep in your outside description, and in throwing away the invisible partner behind the boundary, you transform a pure, entangled state into something that looks thermal, the way a complex chord collapses into a single note when most of its harmonics are muffled. Yet if you gather enough of the outgoing notes over enough time and analyze their relationships, you can, in principle, reconstruct the chord's hidden structure and keep faith with the rule that the universe does not forget. So let this settle softly. A black hole is not a mute sync, but a storyteller with a difficult accent, speaking through a warm whisper that at first sounds like simple noise. And your job as the listener is patience, collect, compare, and connect until patterns emerge. Because in the long run, the glow that seems to blur differences is also the glow that returns them. And there is a quiet comfort in that picture, a cosmos where even the darkest horizons are not vaults that erase but stills that refine. and where the night sky's most secret objects keep time with the deepest law we know, that reality changes shape, but the information about what it has been remains, waiting to be read. Particles as field excitations only. You've been taught to picture nature as a bag of tiny beads rattling through space, so let's start with a sharper image. Imagine an invisible fabric that fills all of reality. One field for light, others for electrons and quarks, still others for neutrinos. And what you call a particle is simply a localized ripple of that fabric, a brief countable packet of excitation that travels, interacts, and then disappears when the ripple is absorbed. And if this sounds like semantics, stay with me because the field-first view clarifies puzzles that the marble picture only hides. When a camera sees a single photon, nothing like a tiny billiard ball has hit the sensor. Rather, the electromagnetic field has driven a microscopic transition in the detector's material, a single avalanche of electrons that your electronics register as a click. And the reason that click is a point rather than a blurred smear is not because the photon was a pellet, but because the detector is nonlinear. It responds in all or nothing jumps, and because the environment quickly scrambles alternative outcomes, leaving one sharp record while bleeding away the rest. So the point-like spot is the footprint of how a field couples to matter, and how information becomes classical, not the true shape of the thing in flight. Now think about how we decide that two particles are the same. Every electron has the exact same charge and mass as every other electron, so exact that no experiment has ever found a difference. And in the field picture, that identity is automatic because there is only one electron field in the universe, and each electron is a ripple of that same entity, stamped by the same rules everywhere. Whereas the bead picture must declare miraculous mass-produced copies with no factory marks to tell them apart. And that miracle quietly becomes a principle once you accept fields. Even the weird way identical particles share space makes more sense now. Excitations of certain fields refuse to pile into the same state, while others love to bunch. And lab results demonstrate both behaviors vividly. The electron shells that give chemistry its structure are a grand architecture built from no two in the same state, while photons in carefully arranged interferometers exhibit bunching that boosts some detection outcomes and suppresses others. A pattern that falls directly out of how field excitations combine, rather than out of any story about tiny pebbles angling past one another. If you've ever wondered why high-energy physics talks so easily about particles being created and destroyed, fields remove the awkwardness. Ripple patterns can be amplified or damped, split or merged, and when two excitations collide and the detector later reports different species on the other side, what has changed is the arrangement of ripples across multiple fields as energy and momentum flow through the interaction. And those mediating effects you hear about are simply the way one field's disturbance stirs another through the couplings that the laws permit, not invisible couriers hand-delivering forces between beads. The field viewpoint also explains why trying to pin a particle to an exact point is a fool's errand. Confining an excitation too tightly forces the field to carry violent variations, which demands energy, and past a threshold the field prefers to pay that bill by sprouting new ripples, what you would interpret as extra particles suddenly appearing. So attempts to lock a thing into a tiny box often end by creating more things, a behavior. That sounds magical only if you started with marbles. Once you shift your attention from objects to modes, stable patterns that a field can adopt given the environment, you unlock a cleaner definition of particle number. Choose a set of modes, and then count how many quanta occupy each mode. And you'll find that your counting depends on which modes you choose, which is not a flaw but a reminder that detectors are designed to speak the language of particular patterns. So what one setup calls one particle, another setup might call a superposition of ripples, much as a melody can be one clear line to your ear, but a sum of many frequencies to an audio engineer. This flexibility pays off in real devices. In a laser, the electromagnetic field is coaxed into a single mode with a large, coherent excitation, and the many photons picture is a useful way to track energy in that mode. While in superconducting circuits, the relevant excitations are microwave ripples guided by lithographed structures that act like artificial cavities, and counting their quanta tells you when you've built a fragile quantum state or accidentally flooded it with noise. The field-first view also demystifies why our best theories predict that interactions have a very specific shape, terms that let certain fields talk to each other and forbid other conversations, entirely because symmetries of the fields act like grammar rules, deciding which sentences of interaction are allowed to be written and which are nonsense. And experiments at colliders confirm those rules with exquisite precision by showing that certain transformations never occur, that others occur with predictable odds, and that conservation laws emerge from those symmetries the way meter and rhyme emerge from a poet's chosen form. Even the story of mass, though we'll explore the dedicated mechanism elsewhere, fits the field frame naturally. A field can drag through a medium that is itself a field, picking up inertia without anyone sticking a literal weight onto a bead, so that what you experience as mass is how hard it is to shake a particular ripple through the background that pervades space. Your intuition might protest that you've seen particles leave straight tracks in cloud chambers and bubble chambers, as if tiny bullets carved the lines. But look closer and you'll notice that each dot and swirl is a chain of discrete interactions, moments where a field excitation dumps energy into the fluid and seeds a tiny wake. And the straightness is the smooth path, traced by the average motion of the wave packet plus a magnetic field's guidance, a macroscopic echo of many microscopic handoffs between the field and matter. If you find yourself asking, then where is the field? The honest answer is that it's everywhere and measurable only through its effects. And the job of physics is to design experiments that convert those effects into records you can trust, which is why particle physics looks like a cathedral of detectors, layered calorimeters, trackers and timing systems that collectively infer which ripples passed by, how much energy they carried, and into which other ripples they transformed when they met. Perhaps the most liberating payoff of adopting fields is conceptual coherence. You stop stapling ad hoc pictures onto phenomena and instead let one principle do the heavy lifting. The world is built from continuously existing entities that can carry energy and momentum in localized, countable packets, and what you call a particle is the event of one such packet being created, moving and being destroyed as revealed by the traces it writes in a measuring device. Let's close softly but clearly. Holding onto the marble picture is comfortable because it matches your hands, but it keeps tripping over facts, from absolute identity to creation and annihilation to the way detection works, and the field picture removes those stumbles while teaching you to design and read experiments with cleaner logic. So the next time you hear that a particle appeared, propagated and decayed, translate it into the language that nature actually seems to speak. A field was excited. The excitation traveled as a mode matched to your apparatus. It interacted with other fields according to the symmetries that govern them. And finally, it left a record when the ripple ended, which is to say you didn't catch a bead. You witnessed the fabric of reality briefly tremble and then become still again. Higgs field, mass as a medium effect. You've heard the folk tale that mass is just how much stuff something has. So let's start with the stranger and truer version. Mass, at least for the elementary building blocks, is how stubbornly certain particles move through an invisible medium that already fills all of space. A medium we call the Higgs field. And the way they gain that stubbornness is not by bumping into grains or syrup, but by existing in a world where this field has settled into a non-zero background value everywhere, quietly reshaping the rules of motion. To enter this without jargon, picture a perfectly still ocean that reaches to every horizon, and now imagine that some boats glide over it as if on frictionless rails while others seem to lean into the water, needing real effort to pick up speed or change direction. Nothing visible pushes back. Yet each boat's design makes it more or less responsive to the water under it, and in our universe, those design features are the strengths with which different particles couple to the Higgs field. When the universe was very hot and young, the Higgs behaved more like a field poised at the top of a hill, balanced and symmetric, and particles moved as if massless. But as the cosmos expanded and cooled, the field rolled into a valley and chose a specific resting place, breaking that symmetry in a subtle, everywhere at once way, and from then on, particles that interact with the Higgs began to carry inertia as if their identity cards now included a built-in resistance to acceleration, while particles that don't interact remained forever weightless. This picture already fixes a common misunderstanding. The Higgs field is not a sticky fluid that drags things, and mass isn't a slowdown due to friction. It's the inertial price tag written into a particle's equations by the constant presence of the field's background value, which means the resistance shows up even when nothing else is around and no motion is happening, exactly what we mean by rest mass. The proof that this is more than a tidy story arrived in 2012, when experiments at the Large Hadron Collider uncovered a new particle, a brief, neutral, spinless ripple of the Higgs field itself, whose properties matched the long-standing prediction. It appears around the energy we label 125 billion electron volts. It decays into pairs of heavy particles and also into photons through loops of heavier actors. And its production rates and branching patterns line up with the expectation that the stronger a particle's interaction with the Higgs, the more strongly the Higgs ripple can morph into that particle and back. Since then, researchers have been weighing this newcomer's traits with growing precision. Its spin is zero. Its couplings scale with mass in a way that ties the whole idea together. And its overall footprint is narrow. The particle dies so quickly that its intrinsic width is tiny, while still leaving enough traces for us to see clear peaks standing out from the noisy background of other collisions. But the Higgs field is not a force we can shield or switch off like magnetism. It is part of the stage on which all the other fields perform. And that brings you to a sobering but liberating distinction. The Higgs mechanism gives rest masses to elementary quarks and leptons, and to the W and Z carriers of the weak force. Yet it is not the direct source of most of your everyday mass, because the protons and neutrons that make up nearly all the weight of your body get their heft mainly from the seething energy of the strong interaction that binds quarks together, a kind of internal storm of gluon fields whose energy registers as mass via Einstein's famous relation. Still, the Higgs matters to you personally in a vital way. Without the electron's Higgs-given mass, atoms could not hold themselves at the sizes and energies they do. Chemistry would be unrecognizable, and stable matter, as we know it, would fail to take shape. So while your bathroom scale mostly weighs confined field energy from the strong force, the possibility of atoms, molecules, and life leans heavily on the Higgs giving electrons and quarks their particular non-zero masses. There's also a cleansing insight into why some force carriers have mass and some don't. Photons remain massless because the part of the electromagnetic gauge symmetry they belong to stays unbroken when the Higgs chooses its resting place. So light keeps its long reach and travels at a universal speed, whereas the W and Z bosons swallow up certain ripples that would otherwise be massless and, in the process, acquire heft and short range. A neat accounting trick that preserves the theory's consistency while explaining why the weak force is weak at everyday distances. As you let these ideas settle, a set of urgent, open questions begins to glow at the edges. Why is the Higgs field's background value what it is, neither zero nor catastrophically huge? Why is the Higgs boson's mass light enough to be found where we found it when quantum effects tend to push it around? Does the field talk to undiscovered particles we cannot yet see? Perhaps one's connected to dark matter? And could the Higgs self-interact in a way that shaped the universe's early history, even helping to tip the cosmos into the matter-dominated state we live in by making the electroweak transition strongly first order? A violent, bubble-forming change rather than a smooth drift, which some theories need to explain why matter survived over antimatter. Experiments are edging into those questions now, measuring the Higgs's self-coupling, checking its whispers to lighter particles like muons, and combing for rare decays that would hint at new sectors, because any deviation from the mass-proportional pattern would be a neon sign that the Higgs is a portal to a wider world. It also pays to clear away another confusion. The Higgs is not a universal mass dispenser for everything you can imagine. Photons and gluons don't get mass from it, and composite objects get only part of their mass this way. So the clean statement is this. The Higgs field endows elementary particles that couple to it with rest mass, sets the range of the weak force, and thereby enables stable atoms and familiar chemistry, while most composite mass arises from confined energy in other fields. Now step back and admire the coherence that the medium idea provides. We didn't bolt mass onto particles like weights on a costume. We discovered that mass is how certain excitations move in a universe where one particular field refuses to be zero. And the Higgs boson is the telltale ripple that proves the medium is truly there. The closing thought is gentle but firm. Mass is not a primitive property carved into matter from the start. It is largely an emergent effect of context, the context being a field that chose a value everywhere, and by measuring how each particle responds to that quiet backdrop, we learn not only why things resist acceleration, but also how deeply the universe is defined by what seems like empty space. A space that, through the Higgs, is anything but empty. And that is why a discovery made in a buried ring outside Geneva reached all the way into your kitchen scale. Because the needle on that scale is reporting, in its own low-tech way, how matter moves in a medium we cannot see, but can now confidently name. 0-point energy in oscillators. You can freeze, quiet, and isolate a system until your instruments all but give up. Then discover it still refuses to sit perfectly still, and that is your doorway into 0-point energy. The unavoidable residual motion and energy that remain even when an oscillator is chilled to its lowest possible state, not because of hidden heat or sloppy engineering, but because the very rules that let the system oscillate also prevent it from becoming exactly motionless. Begin with something tangible like a diatomic molecule, two atoms joined by a spring-like bond, and imagine cooling it toward absolute zero so the atoms stop swapping energy with the world. Classically, you would expect them to settle at the bond's minimum length and rest there forever. Yet high-resolution spectroscopy shows that even in the ground configuration, the atoms still breathe a little, and the molecule's lowest vibrational line sits noticeably above the bottom of the potential well, a shift you can quantify, and that changes with isotope. Replacing hydrogen with its heavier cousin deuterium moves the lines because heavier masses vibrate more sluggishly, but never reach perfect stillness. That simple fact, an offset that persists after all thermal energy is drained, is the signature of 0-point energy, and you can watch its fingerprints spread across very different systems once you know where to look. Superfluid helium refuses to freeze at normal pressure, even near absolute zero, because the atom's ground state jitter is so large that crystallizing would demand a loss of quantum motion they cannot afford. Trapped ions reveal a telltale asymmetry between adding and removing one quantum of vibration when they're driven near their lowest motional state. And nanomechanical beams read out with ultra-sensitive interferometers show a baseline displacement noise that remains even when you duct every classical noise source you can name. To understand why zero is not an option, remember that an oscillator is defined by two linked quantities, call, one position and the other momentum, and the very structure that makes the system oscillate binds these quantities in a way that forbids perfect knowledge of both at once. So if you tried to nail position exactly, momentum would wander wildly, and the act of confining one would dump agitation into the other. The ground state is where this tug-of-war balances most gently. The oscillator finds the smallest compromise allowed by nature, one that still includes fluctuations in both position and momentum, and therefore a non-zero baseline of energy that no cooling algorithm can erase. This is not armchair philosophy, but a design constraint for modern experiments, and you can feel its weight in technologies that live on the edge of silence. The gravitational wave observatories that listen for ripples in space-time have mirrors so quiet and cold that the quantum jitter of light pressing on them becomes a real, measured noise floor, forcing engineers to shape the light's statistical properties to reduce one kind of quantum noise at the expense of another. Superconducting circuits that act as artificial atoms carry microwave resonators whose minimal hum sets how cleanly you can store and retrieve fragile quantum states. And clever techniques like sideband cooling and parametric squeezing are deployed to push motion toward the ground state while acknowledging that a hard floor remains. Even the amplifiers that pick up single photon signals in these circuits face a quantum set minimum noise cost, a tax that traces straight back to the 0-point fluctuations of the modes they couple to. It's natural to ask whether this ever lets you siphon energy from nothing, and the answer is a clear no. The ground state's energy is not a sloshing reservoir you can tap at will. It's the cost of holding the oscillator in a configuration consistent with the rules. and attempts to harvest it merely move energy around by changing the system, altering the potential, the boundary conditions, or the coupling to other modes, and any temporary advantage is repaid once you reckon the full bookkeeping. What you can do, and what experiments routinely exploit, is measure differences, shift the curvature of a potential, and you shift the 0-point level, change the allowed modes, and you change the sum of their ground state contributions. Stiffen a mechanical resonator with an electric field and its baseline motion shrinks. Soften it and the baseline swells. Replace atoms with heavier isotopes and vibrational 0-point energies. Fall in a way that leaves marks across chemistry and materials science. There is an equally important conceptual boundary to keep in sight. While the absolute value of 0-point energy for a single, perfectly isolated oscillator is not an observable quantity, you only ever detect how it changes. When you change the system, sums over many modes in extended systems can have physical consequences when those sums are compared between two configurations, which is why careful theory always asks, compared to what, before claiming an effect. The cleanest pedagogical playgrounds for seeing the ground state in action are systems you can tune and count. A single trapped ion in a harmonic potential shows distinct sidebands when you probe its electronic transition, and the relative heights of those sidebands tell you how much motion remains, with the red process gradually drying up as you approach the ground, and a subtle imbalance persisting that betrays the 0-point flaw. In cavity optomechanics, a tiny drum or beam couples to light trapped between mirrors, and by arranging the laser's color just right, you can coax the light to take energy out of the motion more often than it puts energy in, shepherding the resonator into its lowest state, and then watching how the remaining quantum fluctuations show up as a flaw in the beat note of the scattered light. Scanning probe measurements on molecules and crystals add another set of proofs. Reaction rates, bond lengths, and diffusion barriers all shift in predictable ways when you swap isotopes. And those shifts match the expectations from 0-point energies computed for the vibrational modes involved, showing that chemistry's landscape is quietly reshaped by motion that never turns off. You might worry that this all sounds like semantics for residual heat, but there is a sharp operational difference. Thermal motion can be drained into a cold bath until its fingerprints vanish, while 0-point motion remains when the bath is as cold as physics allows, and it affects systems in proportion to their natural frequency and mass in ways that line up with quantitative predictions. The lesson deepens further when you ask how measurements themselves stir the pot. Any readout strong enough to resolve position very well necessarily pushes back on momentum, and the round trip of probe and response asserts a standard quantum limit for continuous monitoring of an oscillator, a limit not of our ingenuity, but of the linkage between the quantities we insist on knowing at once. And modern labs have reached and even cleverly danced around that limit by measuring special combinations of motion that commute with themselves over time. A finesse move that lets them track one quadrature with less disturbance while letting its partner pay the price. Every item in this catalogue of behaviors, the isotope shifts, the helium that won't freeze, the ground state sideband imbalance, the quantum set noise in amplifiers and interferometers, adds weight to the same conclusion. An oscillator's ground state is not the absence of activity, but the presence of a minimal, structured fluctuation that can't be pressed any lower without breaking the logic that makes the system an oscillator in the first place. So we close with a gentle reframing that will help you think clearly across the rest of this series. 0-point energy is not a promise of free power, nor a mystical ocean waiting to be pumped. It is a flaw built into the architecture of oscillation, and learning to live with, measure, and even choreograph that flaw is part of why today's most delicate experiments work at all. Because when you respect the hum, you cannot silence. You can design around it, sometimes harness its correlations, and always remember that quiet in physics is not the absence of motion, but the presence of the least motion reality allows. Emergence, from microscopic rules to new things. You've spent your life learning that big things are built from small things. So here's a twist that changes how you look at almost everything. At a certain scale, the small things stop being the right language, and entirely new things appear, not by magic, But because countless simple parts following simple rules can lock together into patterns that have properties no single part possesses, and this is what scientists mean by emergence. Begin with something you can feel, temperature, because no single molecule is hot. Each one simply moves, yet take a vast crowd of them and their jostling averages into a smooth quantity you can touch with a thermometer. A number that obeys its own laws, lets you predict pressure and phase changes, and stays meaningful even though it ignores the individual history of each molecule. And this is your first lesson. A good emergent concept forgets most details and wins power in exchange. It lets you coarse-grain reality into a description that actually predicts what will happen next. Now let your eyes watch a flock of starlings as the sky thickens into a living cloud. No bird knows the shape of the flock, none votes on the turns, yet with only local rules, the group becomes a single flying organism that ripples like silk in the wind, and you can build computer models with those minimal rules and recover the same breathtaking choreography. A proof of principle that collective behavior can be computed from micro-instructions without any bird needing a map or a leader. The same logic threads through traffic on a highway. Every driver pursues simple goals. Keep your distance, maintain speed, pass when safe. And yet waves of braking can ripple backward against the flow like invisible shock fronts, even when there is no accident ahead. Patterns you can measure from helicopters or roadside sensors, and even predict with equations that never mention your name, your car, or your favorite radio station. Because once the crowd is large enough, the individual is not the right unit of analysis. If this makes you think, so what? Big crowds are messy. Let's pivot to clean laboratory patterns that emerge as if on cue. Warm a shallow layer of fluid from below, and past a crisp threshold you'll see orderly rolls appear, bright and dark stripes sweeping heat upward and downward in sustained rhythm. A geometry that no single molecule chooses, but the whole layer decides to adopt, because the old, featureless state cannot carry the heat as efficiently anymore. Tweak a chemical gel with two substances that diffuse at different speeds, and you can coax it to grow leopard spots or zebra stripes in a petri dish. A reaction diffusion dance that crafts large-scale motifs from local reactions and wandering molecules without any stencil, and the mathematics that forecasts these patterns never lists the position of each atom. It speaks in fields and rates and thresholds, new nouns for new things. The shift of language matters because it signals a shift of law. When many parts act together, what controls the show are averaged quantities, symmetries, and constraints that only make sense for crowds. And with the right averages, the world simplifies in surprising ways. Liquids flow according to equations that care about density and viscosity instead of the fate of each molecule. A metal bends according to elasticity rather than the positions of atoms. And magnets point because countless tiny spins align and define a large-scale direction we can flip with a modest push. A powerful idea that organizes all of this is universality. The observation that wildly different microscopic details can lead to the same emergent behavior near tipping points. The steam over your kettle and a magnet near the moment it loses its order share the same family of critical exponents that describe how fluctuations explode and correlations stretch across the system. And this sameness is not coincidence but a kind of mercy. At large scales, only general features like dimensionality and symmetry matter. Not whether your molecules are water or carbon dioxide, not whether your spins live on a square or triangular grid. And this is why one set of large-scale equations can rule whole kingdoms of materials. If you want a mental tool for how small-scale mess washes into big-scale order, picture coarse graining, blur the system a little, keep the features that survive the blur, then blur again, and watch how your description flows as you move from fine to coarse views. And if certain parameters march towards stable values while others fade, you have discovered which details the large-scale world cares about and which are safely forgotten. A logic that gives you effective theories. Clean rulebooks for a particular scale that work astoundingly well without claiming to be everything. The joy of emergence is not only that new variables become useful, but that new objects appear that you can measure, manipulate, and reason about as if they were fundamental. Vortices in a fluid spin like tangible threads. Sound waves move through air with their own speed and reflections. Domain walls in a magnet behave like traveling boundaries you can push around. And these entities can even collide, bounce and form bound states, writing a cast of characters the microscopic parts never advertised. If the phrase, "from simple rules to higher order," makes you worry that we're smuggling in purpose, take a breath. Emergence is not a manifesto for destiny. It's a recognition that constraints and feedback create pockets of stability and structure that are favored. And once favored, they accumulate. You can see this in branching rivers that carve fractal maps regardless of local geology, in snowflakes that grow intricate arms without knowledge or design, in the way languages born from human mouths crystallize into grammar you could analyze with rules no single speaker invented, and in the way social norms spread as if they were organisms, rising from local interactions, but acquiring lives of their own, once shared, taught, and enforced. The method remains scientific because it predicts. Once you know the local interactions, the geometry in which they happen, and the energy or information flowing through, you can forecast which patterns are even allowed and which are out of reach, and you can watch experiments cross thresholds you computed and land in states you named beforehand. The most unsettling and fertile territory is where emergent layers push back on their parts, a topic often called downward causation. The rules of chess determine which piece arrangement counts as a checkmate, and that large-scale condition constrains what a pawn can legally do next. Though the pawn's motion still obeys the microscopic physics of wood and friction, the melody in a choir guides each singer's breath and pitch, even though the singer's vocal cords are the true sound makers. A regulation in a city changes the fate of individual commuters while emerging from their collective behavior over years. In each case, the higher level pattern has leverage over the parts without violating the parts' physics. And learning to write laws at that higher level lets you steer outcomes more gently and effectively than trying to micromanage the micro. If you're wondering how to tell genuine emergence from stories we tell ourselves, here's a checklist you can carry into the rest of your life. An emergent description earns its keep when it compresses huge detail into a small set of variables that predict new facts, when it identifies thresholds at which behavior changes qualitatively, when it survives the swapping of many microscopic details, and when it gives you control knobs you can turn to move a system between distinct regimes. It fails when it merely relabels the micro without increasing predictive power, or when it sneaks in purpose where there is none, or when it claims properties that disappear under careful measurement. The practical payoff is enormous. By focusing on the right collective variables, you can stabilize power grids that would be impossible to manage wire by wire. You can forestall traffic jams by adjusting inflow rather than lecturing each driver. You can nudge ecosystems toward resilience by preserving network diversity rather than counting every creature. And you can design materials by aiming for patterns of organization, layering, periodicity, randomness in just the right measure, instead of hunting for a perfect atom-by-atom layout. As you let this sink in, a gentler understanding of explanation itself opens up, saying, the whole is more than the sum of its parts, is not mysticism. It is a claim about the right level of description, about when to stop tracking every grain of sand and start measuring slopes, flows, and thresholds. Because the dunes have their own dynamics and their own mathematics, and learning that mathematics teaches you to predict storms, build safer roads, and read a landscape's history at a glance. So we end softly where we began, with your attention shifting from pieces to patterns. Yes, the world is built from small things, but the story that matters to your senses, your technology, and your choices is often written at higher levels where new nouns are born. Waves, flocks, climates, economies, cultures, and the most empowering habit you can cultivate is to ask, at each problem's doorstep, what is the right scale and the right language here? Because when you choose that wisely, complexity folds into clarity, and entirely new things step forward to be understood, guided, and, sometimes, protected. Symmetry breaking and quantum order. You expect perfect symmetry to be the peak of elegance, but the universe keeps choosing stories where perfection quietly tips and a direction appears from nowhere. This is the doorway to symmetry breaking and the deeper idea of quantum order, where crowds of particles settle on a shared pattern that no single particle could declare. Begin with something you can picture. Heat a magnet until it forgets which way is north. Then cool it slowly and watch as, at a crisp temperature, The spins conspire to point somewhere, anywhere, and once they pick a direction, the symmetry of all directions are equal is gone. Not because an external hand turned the compass, but because the system itself found it easier to live with order than with chaos. And that single choice echoes through every atom as a macroscopic fact you can measure with a cheap sensor. This is spontaneous symmetry breaking, the moment a many-body system trades perfect possibility for a particular reality. You see the same logic in a liquid that becomes a crystal and chooses a lattice, breaking the freedom to slide anywhere into the discipline of repeating positions. A change you can literally see as Bragg peaks in scattering experiments, sharp fingerprints of long-range order. The thread tying these examples is the order parameter, a collective quantity that is zero when the system is disordered and becomes non-zero when order blooms. But the payoff isn't just a new label, it's a new cast of low-energy actors. When a continuous symmetry breaks, there appear soft collective ripples that cost almost no energy to excite, gentle waves of the new order that move through the material like whispers. And even without equations, you've met them. Wiggles of spin direction in a magnet, spin waves, sound like ripples in a superfluid's phase, undulations of a crystal's positions, phonons. These excitations aren't afterthoughts. They are the reason broken symmetry matters. Once order is chosen, the system gains coherence, a kind of rigidity against certain twists, and that rigidity shows up as measurable stiffness, a speed for those waves, and characteristic responses to small pushes. Because the ordering is a collective decision, it doesn't arrive all at once. It nucleates and grows domains, patches that picked different directions. And those patches meet along thin boundaries called domain walls that carry their own physics and can be moved, pinned, or memory encoded by engineers who now treat them as nanoscale features rather than defects. If you want a clean laboratory for watching a symmetry break on demand, look at ultra-cold atoms arranged in laser-drawn egg carton landscapes. Start from a featureless cloud, tune the interactions, and the gas chooses a phase with a defined rhythm. Sometimes a superfluid with global phase alignment, sometimes a Mott insulator with particles locked one per site, and the switch is written into time-of-flight images as patterns of sharp or blurred spots that tell you whether long-range phase coherence exists. The most surprising turn in this story is that not all order announces itself with a simple pattern you can photograph. In quantum matter, there are phases whose order hides in how the many particles are entangled, not in how their average densities arrange, and this quantum order stays invisible to any local snapshot, yet reveals itself in global tests and at the edges. Famous examples carry currents along their boundaries, while the interior remains insulating, or host excitations that refuse to be mimicked by any collection of ordinary particles. And the remarkable thing is stability. You can rough up the surface, swap impurities, or bend the sample, and as long as certain symmetries or overall winding properties are preserved, the special edge behavior refuses to die. This introduces two flavors of quantum order you can keep straight without math. Topological order, where the ground state is tied in a way that can't be undone by gentle prodding and often supports exotic boundary modes, and symmetry-protected topological phases, where the magic persists only while particular symmetries are respected, like a melody that holds as long as musicians keep the beat. Detecting such order means asking smarter questions. Do edges conduct in a way the bulk does not? Do certain defects trap states that shouldn't exist in a trivial material? Do interferometry loops pick up phases that reveal hidden structure? And does the system remember which sector it occupies even when you change its microscopic details? This shift from "what pattern do I see" to "what can the system do that a trivial one cannot" is the heartbeat of modern condensed matter physics. And it has real consequences. Robust edge channels resist scattering and promise low-loss electronics. Protected boundary states encode information that laughs at local noise. And domain walls and vortices become handles we can grab to move, store, or compute with quantum bits. Symmetry breaking also rewrites which forces reach how far. Once a system picks a direction or a phase, certain fluctuations become costly while others remain free, reshaping the spectrum of what can happen. And the new balance explains why some materials carry waves cleanly while others damp them. Why a gentle twist can propagate through a crystal across millimeters, and why a slim magnetic pulse can flip an entire micron-size region with a tiny kick. None of this requires you to abandon humility about microscopic truth. Atoms and electrons still follow their fundamental laws, but it invites you to respect the autonomy of higher-level rules. When many degrees of freedom synchronize, new regularities close over the details and earn the right to be called laws in their own range, and it warns you away from a common trap. Not every apparent pattern signals a broken symmetry. Some arise from kinetics, constraints, or disorder, and distinguishing true phases from fleeting imitations is what careful measurements, finite size scaling, and reproducible thresholds are for. In the end, symmetry breaking gives you a narrative for how featureless possibility narrows into tangible order, while quantum order expands that narrative to include phases that carry identity without visible pattern, and together they change how you design and reason. You don't ask only, what are the parts, but what can they agree on? What stays rigid when I poke it? And what new low-energy characters appear once a decision is made? And when you learn to ask those questions, you start to see the world's quiet revolutions. The instant a material chooses a direction, the birth of waves that move almost for free, the edges that act differently from the interior, and the hidden bookkeeping that keeps these features stable even when the surface looks ordinary. And you close the day with a calmer mind, knowing that perfection breaking is not a failure, but a beginning. The moment laws appropriate to the many take over from the language of the few. Kibble Zurek, freezing patterns out of nothing. You're told that order needs a blueprint, but here's a more rebellious truth. If you rush a system through the right kind of change, patterns can freeze into existence with no architect at all, as if structure crystallized straight out of nothing. And this is the heart of the Kibble Zurek story. When the rules of a material shift faster than the material can keep up, islands of decision form, collide, and leave behind scars called defects whose density remembers how hard you pushed. To see why, picture a landscape that gradually reshapes itself as you turn a single dial. Temperature, pressure, magnetic field, and imagine that, at a particular setting, the material is balanced on a knife edge where fluctuations swell and the time it takes to settle grows longer and longer, a slowdown so dramatic that near the tipping point, the system cannot respond quickly to your turning anymore. So whatever local choices have started to form become frozen, unable to coordinate across the whole sample. Regions that fell into different alignments then meet, and where they disagree, the compromise is not to erase history, but to trap it. A domain wall between alternate orientations, a vortex where a phase winds around and cannot be unwound. A line-like string threading the material. In short, topological defects. The footprints of decisions made without consultation. Kibble's original insight came from cosmology, with the early universe cooling through symmetry changes so quickly that distant patches could not agree on the same setting, potentially seeding cosmic strings and other relics, while Zurek translated the logic to the lab, arguing that superfluid helium, superconductors, liquid crystals, ion crystals, and ultra-cold gases should all leave measurable debris when quenched through continuous phase transitions, and crucially, that the number and size of those defects should follow a simple scaling with how fast you cross the transition. Slower sweeps give the system time to coordinate and produce fewer, larger domains. Faster sweeps break the world into many small, mismatched patches crowded with defects. This isn't just storytelling. Experiments have spent decades chasing and then catching the scaling. In superfluid helium, rapid cooldowns leave behind quantized vortices whose areal density grows with quench rate. In superconducting rings, sudden passes through the critical temperature trap. Random magnetic flux quanta, tiny loops of field whose statistics reveal how sections of the ring chose incompatible phases before they could communicate. In liquid crystals, cooling thin films generates a tangle of line defects. You can literally image between crossed polarizers, and their density follows the predicted trend as you vary the cooling ramp. Trapped ion chains present a cleaner theatre still. By tuning the trap, so a straight line of ions prefers a zigzag arrangement, researchers see topological kinks appear where one domain's zigzag meets the mirrored pattern of its neighbor, and by changing the speed of that structural transition, they measure how often kinks pop up. matching the Kibble-Zurek rate law with enviable control. Ultra-cold atomic gases add another class of proof, with two-dimensional Bose gases forming vortex-antivortex pairs after fast quenches, and tunnel-coupled condensates, imprinting phase patterns whose defects count how uncoordinated the two sides remained as they were stitched together. Under the hood, there are only a few moving ideas, and you can keep them without equations. As you approach a continuous phase transition, information takes longer to travel because the system's internal relaxation time balloons, a phenomenon called critical slowing down, and there's a length, the correlation length, over which pieces can act in concert. When your external dial sweeps too quickly, there's a moment when the system falls out of equilibrium. Call it the freeze-out time, after which local patches can no longer stay in step with the changing rules, and the correlation length at that moment sets the typical domain size that will survive after the dust settles, since the number of domains roughly sets the number of defects that must snake between them. The defect density inherits a power law dependence on how fast you cross the transition, a surprisingly universal recipe that depends only on how stiffly correlations grow and how sharply the dynamics slow, the two fingerprints that define the transition's universality class. What makes this mechanism more than a curiosity is its reach. It gives you a ruler for nature's handwriting at birth, and it gives engineers guidelines for both avoiding and exploiting disorder. Cool a superconducting circuit too quickly, and you can accidentally trap flux that spoils its performance, but quench a material intentionally and you can plant a design network of domain walls or vortices that act as memory bits, waveguides, or pinning centers. Even quantum computing takes notes here. Adiabatic algorithms and quantum annihilers try to steer a many-body system through a landscape of minima without exciting defects. But the Kibble-Zurek lens says your schedule must slow down near critical points, or you'll freeze in the wrong answers. And recent devices actually map their error patterns onto Kibble-Zurek predictions to refine how they ramp controls. You might ask whether this is all just leftover mess rather than law, but the beauty of the mechanism is precisely that the mess is law-governed. Repeat the same quench protocol again and again, and the individual defect positions will change. Yet the statistics of how many appear and how far apart they tend to be will lock in, and sweeping more slowly will predictably clean the canvas. And you might worry whether discontinuous transitions, where systems jump rather than glide, fit this mold. There the metaphor changes, because the speed limit is set by nucleation events and growth rates rather than critical slowing down, so Kibble-Zurek's neat scaling does not apply, a reminder that not every pattern born in a hurry is born the same way. There are still frontiers, in materials with long-range interactions, or in driven and disordered systems far from equilibrium, the naive scaling can warp. And in topological phases, the defects may be exotic edge modes, whose counting requires more subtle probes, yet the organizing question remains the same. How far can a system coordinate under a changing rulebook before time runs out, and every year brings sharper experiments that measure that coordination length directly in space and time? Let's end where the idea earns its poetry. You do not need a sculptor to get sculpture. If you change the conditions faster than communication allows, the world commits to different answers in different places, and where those answers collide, reality makes seams that can carry current, store bits, guide waves, or simply stand as fossils of a moment when becoming was faster than agreeing. And once you've seen that, you start to recognize Kibble-Zurek fingerprints everywhere. From the crack patterns in cooling glass to the swirl left in a hastily stirred superfluid. And you learn a calm, practical humility. If you want clean order, slow down near the moment it matters. If you want useful complexity, choose your rush with care. Quantum criticality. Phases at the brink. You're used to phase changes being about temperature. Ice melts. Magnets demagnetize, so here's a sharper edge to stand on. There are transitions that happen not because you heat or cool, but because you twist a non-thermal knob like pressure, chemical composition, or magnetic field until the ground state itself flips. And right at that zero temperature tipping point, the system becomes quantum critical, a place where fluctuations are so deep that time joins space as part of the pattern and ordinary. Quasi-particles give up their starring roles. To step into this without equations, imagine a material with two competing orders. Say, a magnet that wants its spins aligned and a paramagnet that wants them restless, and you compress it just enough that neither preference wins cleanly at absolute zero. Then even a whisper of heat reveals the stalemate as a fan-shaped region in the phase diagram, where the fingerprints of the quantum brink leak upward to finite temperatures. Response functions lose their usual energy scales. Spectra collapse when plotted against simple combinations like frequency divided by temperature and familiar rules of metallic life. Constant resistivity offsets, neat electron-like heat capacity, unravel into strange metal behavior where resistance can grow in a line with temperature, and the very notion of a long-lived electron becomes suspect. The reason this feels so different from everyday critical points is that quantum mechanics supplies the fluctuations instead of thermal jostling. And those fluctuations extend not just across distances, but across durations. So the correlations that define the critical state knit together events separated in time, much as classical criticality knits together regions in space. Which is why experimentalists talk about a dynamical critical exponent that tells you how time and length scale together, and why theorists often reach for field theories that respect scale and sometimes even conformal symmetry to describe the brink. You can hold this in your hands in several families of materials. Heavy fermion compounds, where F electrons hybridize with conduction electrons, can be tuned by pressure or chemical substitution to a point where magnetic order dissolves, and the metal that remains refuses to behave like a gas of tidy quasi-particles. Copper oxide superconductors, stripped of their high-temperature superconductivity by fields or overdoping, slide into regions where transport looks Planckian, as if the shortest allowable relaxation time set by quantum mechanics is being used at every opportunity. Iron-based superconductors draw similar maps, with pneumatic or magnetic orders giving way under pressure and leaving behind broad fans where anisotropies soften and collective modes go critical. In thin disordered films, the superconductor-insulator transition at low temperatures can be driven by a magnetic field, and right around the critical field, scaling collapses of resistance against temperature and field tell you the system has lost its intrinsic scales. Even cold atoms in optical lattices, cooled and organized by laser light, have let us watch the superfluid Mott insulator transition in 2 or 3 dimensions, with measurements of compressibility and sound-like modes tracing the same scale-free logic that solid-state labs learn to read from heat capacity and neutron scattering. If you want a minimal cartoon to anchor your thoughts, the quantumizing chain in a transverse field offers it. At weak field, the spins choose an order. At strong field, they align with the drive, and in the knife edge between, the excitations are neither simple spin flips nor simple field quanta, but critical fluctuations that spread in space and time with no characteristic length, a behavior simple enough to solve exactly yet rich enough to teach the broader lesson. At the brink, the system forgets microscopic details and remembers only symmetry, dimensionality, and dynamics. The experimental signatures feel like a checklist once you know them. Specific heat that picks up logarithms or unusual power laws instead of tidy linear in temperature coefficients. Magnetic susceptibility that refuses to saturate. Neutron spectra that show broad continua rather than sharp particle-like peaks, and often collapse when plotted versus frequency over temperature. NMR relaxation rates that refuse to follow standard metallic trends, and thermal expansion, or magnetocaloric responses that diverge in ways you can tie directly to how the entropy piles up near the critical manifold. Transport is where quantum criticality has made headlines because of its practical bite. Linear in temperature resistivity over decades of temperature, Hall angles and magnetoresistance that follow scale-free forms, and damping rates so large and so universal across families that many researchers suspect a bound on how quickly information can scramble in a material, the so-called Planckian bound, is being flirted with, not as a coincidence but as a general feature of life without quasi-particles. If you're wondering how order can disappear in more interesting ways than a simple competition, modern work has delivered an answer called deconfined quantum criticality, where 2 incompatible orders, say antiferromagnetism and a valence bond crystal, are separated not by a first-order jump but by a continuous transition whose critical theory features new fractionalized degrees of freedom that never appear as isolated particles on either side, a reminder that the brink can host actors. The stable phases do not, and that the path between phases can be more telling than the phases themselves. All of this might sound rarefied until you notice how it feeds design. If you want high-temperature superconductivity, you often find it perched near a quantum critical point where glue from critical fluctuations, or simply the breakdown of competing order, makes pairing favorable. And if you want to avoid noise and instability in quantum devices, you learn to stay clear of brinks where slow, scale-free fluctuations bleed into your qubits as low-frequency noise. Equally, if you want to simulate complex quantum matter with cold atoms or programmable quantum platforms, you aim straight for critical points, because that is where the universal physics is most legible, and the need to know every microscopic parameter is least pressing. There are cautions, and learning them makes you a better reader of data. Not every linear resistivity is proof of quantum criticality. Disorder and phonons can mimic parts of the story. So the strongest cases marshal multiple probes and look for scaling collapses, entropy pileups, and tunable crossovers that map the fan cleanly. Not every zero-temperature endpoint is second order. Sometimes the system tunnels from one state to another via a first-order jump, and then the rich scaling and strange metal behavior will be absent or sharply curtailed. And not every candidate is governed by the simplest frameworks that treat critical modes as gentle fluctuations of order parameters. Sometimes the electrons themselves participate so violently that you need beyond standard descriptions where the very notion of a small parameter fails. The conceptual payoff you can carry forward is simple and powerful. A quantum critical point is a place where the ground state is delicately balanced, and because quantum mechanics weaves time into the fabric of the fluctuations, that balance spills its character up the temperature axis, creating a wedge where ordinary excitations die and the material speaks in scale-free accents. The practical habit that follows is to read phase diagrams with new eyes. Look for the axis that is not temperature. Look for the cusp where two phases meet at zero temperature. And then look up and out for the fan whose interior measurements, heat, magnetism, scattering, transport, lose their preferred scales and can be collapsed onto one another by the right rescaling, and we can close gently by returning to your intuition about order and change. The brink is not just a cliff where you fall from one phase to another. It is a high plateau where the view is unexpectedly wide, where the details of the ground fall away, and the geometry of possibility itself becomes visible. And once you've learned to recognize that plateau, in metals that forget how to be metals, in magnets that hesitate between alignments, in ultra-cold gases that weigh the choice between flow and lockstep, you start to see why frontier materials cluster near it. Because at the brink, new rules are loud, old rules are quiet, and entirely new behaviors become thinkable, measurable, and sometimes useful. Superfluid helium's quantum whispers. You think liquids all follow the same rules: pour, splash, slow down when squeezed. So the first time you meet superfluid helium, your intuition trips. Cool ordinary helium below a thin blue line at 2.17 Kelvin, the lambda point, and the liquid sheds most of its viscosity as if it remembered how to flow without friction, creeping up and over container walls in whisper-thin films, slipping through capillaries that stop any normal liquid, and carrying heat in a way that looks less like conduction and more like a coordinated migration. To see why this isn't a magician's trick, start with the fact that helium atoms are exceptionally light and weakly attracted to one another. And even at temperatures where every other element would lock into a crystal, helium's zero-point motion, the unavoidable quantum jiggle of each atom, keeps it fluid, which is why at ordinary pressure helium refuses to solidify even if you cool it to nearly absolute zero. A hint that quantum rules will not stay politely in the background here. Just below the transition, the liquid behaves as if it were two interpenetrating fluids. A normal component that carries entropy and behaves like an ordinary liquid, and a superfluid component that carries no entropy and flows without resistance. Press gently on one side of a porous plug that filters out the normal part, and the superfluid alone will stream through. A superleak that proves you can separate the two behaviors in practice, and heat this system unevenly, and you'll see the famous fountain effect, where the temperature difference drives the superfluid toward the warmer side and pushes liquid upward like a soft, continuous geyser. Move from pictures to measurements, and the story sharpens. Twist a stack of razor-thin disks in a torsional oscillator, and you'll find that, as you cool through the lambda point, less of the helium wants to be dragged along by the rotating stack, because the superfluid fraction decouples from the motion and stops contributing to the inertia. A clean way to weigh how much of the liquid has taken on the new, frictionless roll. Send a carefully shaped thermal pulse through the liquid and you'll detect not just ordinary sound, but second sound, a temperature entropy wave where the superfluid and normal components slosh past each other in opposite directions, carrying heat at blistering rates that make superfluid helium the coolant of choice in exotic places, stabilizing superconducting magnets, nursing ultra-cold stages in space telescopes, and transporting heat away from instruments with a quiet efficiency engineers dream about. Probe the flow a little harder, and you'll hit another defining rule. When superfluid helium swirls, it can't generate messy, continuous eddies the way a classical liquid does. It must form quantized vortices, thread-like lines where the liquid briefly gives up being irrotational, and the circulation around each line comes in fixed packets. So a rotating bucket of superfluid fills with a tidy lattice of these quantum whirlpools, a behavior captured directly in experiments that visualize the tangle with tracer particles or track how sound scatters. And if you stir hard enough, you can generate quantum turbulence, a forest of vortices that crash, reconnect and decay by radiating waves, an entire subfield where turbulence is not a featureless roar, but a choreographed tangle you can count. The disguise that keeps all this coherent is the liquid spectrum of low-energy excitations, long-wavelength phonons and short-wavelength rotons that set a critical velocity. Drift slower than this, and the superfluid can't easily shed energy into excitations, so it keeps gliding. Push faster, and you open channels for the liquid to make phonons and rotons, turning on dissipation and reminding you that frictionless has a domain of validity. No perpetual motion machines here, just a new kind of perfection with clear boundaries. Step sideways into helium-3 and the quantum whisper changes key. Helium-3 atoms are fermions, so they can't all pile into the same one-body state the way helium-4's bosons can. And yet at temperatures 1,000 times colder, mere thousandths of a Kelvin, they pair up into delicate, extended molecules and condense into a superfluid with p-wave character, a cousin of unconventional superconductors, where the order parameter has direction and texture. And this paired superfluid comes in distinct phases with different symmetries and topological features, supporting exotic surface states and textures that have become a playground for testing ideas about topological matter under exquisitely controlled conditions. Back in helium-4, the strange, creeping film that climbs beakers and bridges gaps, Rollin film, stays thin yet defies gravity because the surface energy plus superfluid mobility let it flow until levels equalize, which is both a wonder and a nuisance. Beautiful in demonstrations, fussy in lab practice, because superfluid helium will quietly escape from unguarded containers along any wettable path. The same light quantum nature that keeps helium fluid also sets practical limits. While we speak of zero viscosity, that's a DC. Ideal, drive the liquid at high frequencies or through rough enough environments, and you reintroduce channels for dissipation. And at finite temperatures, the normal component is always there as a partner, producing mutual friction with the vortex lines and giving designers a real-world set of knobs to tune rather than a fairy tale. String a narrow, weak link between two superfluid reservoirs, a nano-fabricated constriction or an array of tiny apertures, and you can observe a Josephson-like effect for mass flow, with oscillations that map directly to the phase difference of the superfluid across the link. A quantum interference device not for electrons but for atoms, and ring-shaped channels can trap persistent currents that wind around for hours or days, quiet gyroscopes sensitive enough to feel minute rotations, hinting at metrological tools that trade electromagnetic fuss for the serene discipline of neutral quantum flow. Because helium stays liquid so far down in temperature, it has become the solvent of choice for reaching the coldest, cleanest regimes in physics. dissolving a pinch of helium-3 in helium and then separating them in a dilution refrigerator pumps away heat in a continuous cycle. The workhorse of laboratories that measure single electron devices, fragile qubits, or ultra-quiet mechanical resonators. Superfluid helium also teaches humility through apparent discoveries that later soften. Early reports of a supersolid phase, solid helium with a fraction that flows without friction, sparked excitement when torsional oscillators seemed to show a mass drop at millikelvin temperatures, as if some of the solid decoupled from rotation. But years of careful control experiments revealed that much of the signal came from subtle stiffening of the solid helium and the oscillator itself. Not frictionless flow, a reminder that in this field, extraordinary claims must survive extraordinary housekeeping. Even so, helium in porous media and on atomically thin films continues to reveal borderline states where confinement, disorder, and quantum statistics tug in opposite directions, producing glassy dynamics, pinning of vortices, and modified superfluid responses that teach us how quantum order negotiates rough terrain. What makes superfluid helium such a reliable teacher is the way it turns abstract principles into grab-and-turn knobs. The two-fluid picture becomes visible in a fountain tube. The quantization of circulation becomes visible in a rotating bucket. Second sound becomes audible to the right sensor, and the critical velocity becomes measurable with a moving wire or an aperture, so that you can map the entire landscape from kitchen sink demonstrations to national lab precision. Carry two closing habits with you from this quiet marvel. First, whenever a system looks smooth, ask what its low-energy excitations are and what symmetries they respect, because those two answers will tell you what frictionless really means and when it will break. Second, remember that not all order is rigid like a crystal. Some order is phase coherence, a collective agreement written across millions of atoms, and once that agreement is in place, flows that would normally grind to heat can glide for extraordinary distances, guided by rules simple enough to state and subtle enough to fill a career, which is why a puddle that looks like any other becomes, a few degrees above absolute zero, a textbook that whispers how quantum mechanics redefines the word liquid and, with it, your sense of what matter can do when it moves together. Cooper pairs, electrons that dance in sync. You've been told that electrons hate to crowd, that like charges repel and scatter, and yet the quiet miracle at the heart of superconductivity is that, under the right conditions, electrons form delicately bound pairs that move as if they share one mind. And once you see how that dance begins, you stop thinking of metal as a billiard table and start hearing it as a hall where rhythm matters. Begin with a crystal at low temperature, its atoms arranged in a regular lattice that can flex ever so slightly, and picture one electron passing through. It tugs the positive ions a hair toward its path, leaving behind a tiny wake of denser charge. Another electron arriving a moment later is drawn toward that wake, and although the two electrons still repel, the lattice-mediated attraction can outweigh the direct push for a narrow band of momenta and energies, allowing the pair to bind at long range, not as two particles orbiting like planets, but as a correlated state spread over hundreds or thousands of lattice spacings, a whisper of cooperation in a sea that previously looked purely competitive. This is the first surprise you need to absorb. A Cooper pair is not a tight molecule. It's a diffuse partnership stabilized by the collective properties of the whole Fermi sea, and once one such pair can exist, the stage is set for many to form and to lock their phases together, trading individualism for a choreography that resists disruption. What changes so profoundly when pairs condense is the system's energy landscape. Instead of a tangle of single electron states available right at the metal's operating energy, there opens a clean gap, an energetic no man's land, that isolates the paired ground state from the first allowed broken pair excitations, and this gap is the shield that protects motion from ordinary scattering. Nudge a normal metal and electrons deflect off impurities and vibrations, turning electrical energy into heat, but nudge a superconductor and you find remarkably little to push against. Because to scatter in the usual way you would have to break pairs across the gap, and at low enough temperature there simply isn't the thermal budget for that. So the current flows with a persistence that feels uncanny. Start it, and it does not readily stop. This picture earns its credibility from experiments that measure the consequences directly. Tunneling spectra show the missing states in a neat, U-shaped depression flanking sharp onsets where broken pairs finally appear. The specific heat jumps at the transition because the system suddenly reorganizes what kinds of excitations it can host. And the response to magnetic probes reveals that most conventional superconductors adopt spin-singlet pairing too. Electrons with opposite spins, since the night, shift in nuclear magnetic resonance, falls when spins pair off and become less available. To align with an external field, the fact that atomic mass influences the transition temperature, known as the isotope effect, ties the whole story back to the lattice, because heavier ions vibrate more sluggishly, and that softens the mediating attraction, dropping the temperature at which pairing locks in. A subtle but clean signature that the heartbeat of the crystal is part of the glue. Now your instinct may protest, if pairing is so delicate, why isn't it instantly destroyed by the inevitable dirt and complexity of real materials? And the answer is that while magnetic impurities are indeed ruthless pair breakers, because they flip spins and scramble phase, ordinary non-magnetic disorder is surprisingly tolerable for conventional S-wave pairing, a robustness that underpins the use of superconducting wires and thin films in messy, real-world environments. There is a geometric side to the story as well. The coherence length, a measure of how far the paired state stretches, can be enormous in soft, low transition temperature metals, tens to thousands of nanometers, signaling that each pair samples a vast swath of the crystal and is therefore blind to tiny bumps. In other families, the length shrinks dramatically, hinting that pairing is stronger and more local, and that shift opens the door to unconventional behavior. Step into the high-temperature superconductors, and you find that pairing survives at temperatures once thought impossible for this phenomenon. But the glue is no longer a gentle lattice vibration you can point to with a single parameter. The gap can have nodes where it vanishes along specific directions, revealing a sign-changing structure in momentum space. And phase-sensitive experiments, interference loops and corner junctions, prove that the order parameter behaves like a tilted clover rather than a uniform disk, a geometry that damps simple scattering and encourages more exotic collective modes. Ion-based superconductors add their own twist, with multiple electron and hole pockets around the Fermi surface, and evidence that the pair wave function changes sign between them, suggesting that magnetic fluctuations, not just lattice vibrations, can mediate attraction. These differences matter because they alter how the pairs respond to disorder, how they trap magnetic flux, and how they carry heat, painting a zoo of materials where one pairing to rule them all is replaced by a toolbox of mechanisms tuned by chemistry and structure. Yet amidst that diversity, certain fingerprints persist. The gaps opening and closing across the transition, the collective stiffness of the paired state against twisting its overall phase, and the remarkable resilience of current once it starts. It helps to carry a mental image that balances poetry and precision. A Cooper pair is best seen as a coherent pattern, a coordinated arrangement across the many electron states at the top of the Fermi sea. So when you accelerate the superconducting condensate, you are not pushing beads through a sieve. You are shifting the phase of a macroscopic wave function, and the system answers as a whole. From this vantage point, many classic observations become less mysterious. The way thin films can carry astonishing current densities if you keep magnetic fields at bay. The sudden collapse of pairing when you sprinkle in enough magnetic atoms to shatter coherence. The distinct threshold above which high-frequency fields or strong currents start to break pairs and restore dissipation. And the emergence of collective excitations, amplitude and phase modes of the order parameter that can be driven and probed by clever pulses of light. If you're tempted to ask whether all pairing must be between opposite spins, the answer is a qualified no. Most known superconductors are singlet, but there exist triplet candidates where spins align, opening a route to long-range proximity through ferromagnets and to exotic edge states that mimic particles with unusual statistics. And while the definitive catalogue is still being written, experiments on certain ruthenites, heavy fermions, and engineered heterostructures continue to test whether pairs can carry internal angular momentum that bends the usual rules. Your practical takeaway is that pairing is a designable phenomenon. Soften a lattice mode, sharpen certain magnetic fluctuations, increase the density of states, or adjust dimensionality, and you tilt the odds in favor of electrons finding that narrow corridor where repulsion is sidestepped and a collective energy saving is possible. Your philosophical takeaway is quieter. What looks like impossible cooperation at the level of two charges becomes inevitable once you let the whole environment into the conversation, because the lattice, the sea of other electrons, and the symmetry constraints change the meaning of interaction from a simple push to an intricate negotiation. And the pair is the signed agreement. We close gently with a habit that will serve you across all of quantum matter. Whenever a system exhibits a loss of friction, a resilient flow, or a sudden opening of stability, ask whether you are witnessing the birth of a coherent order with a gap protecting it. And if you are, listen for the faint rhythm of pairing underneath. Because in the right light, a superconductor is not a colder metal but a choir. And the reason its song carries so far is that its singers are in pairs, holding one note together so firmly that ordinary noise can't make them let go. Superconductors and flux quantization. You don't expect a metal to count in whole numbers, but the simplest superconducting loop does exactly that. Thread a magnetic field through a cooled ring, and it will accept that field only in discrete packets. Single flux quanta, as if the loop were a turnstile clicking integers, and the clicks are so stubborn that they survive dents, impurities, and the quirks of chemistry. To feel why a material can suddenly care about whole numbers, start from the fact that a superconductor is not just a better conductor. It is a phase-coherent state described by a single, well-defined quantum phase across macroscopic distances. And when you take that phase for a lap around a closed path, it must come back to itself without a mismatch, which forces the magnetic field linked by the path to adopt values that make the phase wind by an integer number of complete turns. No more, no less. This is the quiet origin of flux quantization. The evidence is as concrete as it gets. In the early 1960s, tiny hollow cylinders cooled below their transition temperature responded to an applied field by settling into states where the magnetic flux trapped inside took discrete values, one quantum apart. And as the field was swept, the cylinders stepped between adjacent integers rather than sliding smoothly. A benchtop signature that macroscopic matter had begun to obey a counting rule usually reserved for atoms. Once you accept that the phase is in charge, a cascade of consequences becomes legible, starting with the Meissner effect's deeper message. A superconductor doesn't merely carry current without resistance. It actively expels magnetic field from its interior, bending currents along its surface to cancel the field inside. And this expulsion is nearly perfect until the field grows strong enough to force its way in through narrow, thread-like cores, vortices, that each carry exactly one flux quantum. So a so-called Type II superconductor under moderate field is not partly superconducting and partly normal in a vague way, but a clean lattice of quantized, whirlpools threading an otherwise superconducting sea. You can photograph that lattice directly with techniques like decoration or scanning probes, and literally count the quanta, watch them march as the field increases, and see them jostle when you push a current. If defects pin them in place, the material can carry huge currents with little loss. But if vortices move, they drag energy, and you feel a resistance called flux flow, which is why engineers spend real effort planting nanoscale pinning sites to immobilize those threads and keep magnets in MRI machines and particle accelerators rock steady. Move from bulk to loops, and the quantization takes on new roles. Cool a superconducting ring through its transition in a magnetic field, and it will trap the nearest integer number of flux quanta, then generate a persistent current to defend that choice. A current that can circulate for hours or years because there is no ordinary friction to drain it. And as you vary the field ever so slightly, the ring will wait, and then snap to the next integer, a kind of digital memory written by geometry. Shrink the ring to the nanoscale and you uncover the little Parkes effect, where the transition temperature itself wiggles periodically as you change the enclosed flux, because the energy cost of twisting the phase depends on how far the actual flux is from an integer multiple of the quantum, offering a clean, purely thermodynamic readout of phase winding. Cut a tiny weak link into the loop and the story deepens again. A superconducting quantum interference device is nothing more than a loop with one or two such links, and its total current becomes an exquisite function of the phase difference around the loop, which magnetic flux controls. So changes in field as small as a few millionths of a flux quantum translate into measurable changes in current or voltage. This is why SQUIDs can map the faint magnetic fields of your heart and brain, listen to the whisper of geological structures deep underground, or stabilize qubits whose states are encoded in the direction of a persistent current. The same counting rule reaches into metrology and the new SI. Because the size of one flux quantum depends only on two fundamental constants, devices that step in exact multiples of that quantum tie practical measurements to nature's fixed numbers, which is why Josephson junction arrays define voltage standards, and why quantum electrical metrology now rests on rock-solid relationships rather than artifact objects. In real materials, the simplicity is durable but not naive. The magnetic field doesn't drop to zero at the surface in a cliff. It decays over a short penetration depth, and the coherence length sets how quickly the pair wave function heals if it is disturbed. And the ratio of these two lengths decides whether a superconductor is type Y or type 2, a dichotomy that lets you choose the right alloy for a given job. Pure lead makes a lovely type I demonstrator, while niobium titanium and high-temperature ceramics are classic type 2 workhorses. Narrow wires and ultra-thin films add their own twist. When the cross-section is so small that the phase can slip by a whole turn at a localized spot, you can observe phase slips that momentarily relax the counting rule and give a tiny resistance even well below the transition, a quantum version of a hiccup that matters in nanoscale sensors and in the design of ultra-low-loss circuits. All of these effects reinforce a single habit of thought. In superconductors, the phase of the macroscopic wave function is a real, measurable player and geometry, whether a loop, a grain boundary, or a landscape of defects, teaches that phase how to wind, lock, or slip, which in turn dictates how magnetism threads the material. From an applications point of view, flux quantization is not a party trick, but a toolkit. It enables magnetometers so sensitive they can see neural activity through your skull, allows flux-based qubits and logic elements to count and control their own states with digital clarity, and provides a way to store energy as a persistent current without leakage in experimental power devices. From a conceptual point of view, it is one of the cleanest bridges between the microscopic and the macroscopic. A counting law born from the requirement that a quantum phase be single-valued ends up setting how a bulk piece of metal admits magnetic field, how it carries current, and how a loop chooses its state in integers, so that by the end of the day, you've learned to stop treating magnetism inside a superconductor as some field lines here and there, and start treating it as a set of indivisible threads and packets. And once you see those packets, you can design with them, measure with them, and just a little, think with them. Because a metal that clicks in whole numbers is telling you that coherence is not a metaphor, but a rule the world will follow if you cool it, shape it, and listen closely enough. Macroscopic quantum phases. You don't usually think of a single electrical phase as something you can point like a camera, yet that is exactly what we do when we turn macroscopic quantum order into an eye on the invisible. Build a small loop of superconductor, let its collective phase wrap around, insert one or two weak links that are sensitive to that phase, and you've made a SQUID, a device that turns the faintest magnetic murmurs into voltages we can read, as if the quiet of a cooled metal had learned to see. Begin with the conceptual leap you've earned. A superconductor isn't just good metal, it's a single, coherent state that carries a well-defined phase across macroscopic distances, and when you create a loop, the phase is forced to be consistent after a full lap. So any magnetic field threading the loop must be balanced by a matching twist of phase. The weak links, tiny barriers where pairs tunnel, act like translators, turning a change in phase into a change in current. And because the loop's phase depends on the threaded field, the whole device becomes a phase-to-voltage converter for magnetism. That is the essence of a SQUID sight. But vision needs stability. So practical instruments place the SQUID in a feedback embrace called a flux-locked loop. The moment the device senses a change, electronics, inject a compensating magnetic signal through a miniature coil to push the phase back to a chosen operating point, and the amount of feedback required becomes the output, linear and stable over a vast range where the raw quantum periodicity would otherwise produce a sawtooth. Two flavors dominate the toolbox. The direct current version, with two junctions in a loop, yields a smooth oscillation of voltage with magnetic flux when you bias it with a gentle current, while the radio frequency version, with one junction, is embedded in a resonant tank and probed with a carrier tone, letting you read out changes as tiny shifts in impedance. Both achieve sensitivities that can register fields 1 trillion times weaker than a fridge magnet, not by brute amplification, but by exploiting the discipline of phase in a quiet, cold environment. To appreciate what that sensitivity buys, step into a shielded room where the walls swallow the city's electromagnetic chatter and ask a SQUID to listen to you. Your brain generates minute magnetic ripples as neurons fire in synchrony, and arrays of SQUIDs, magnetoencephalography, draw maps of that activity millisecond by millisecond without ever touching you, localizing epileptic foci for surgeons, or tracking how auditory and visual areas talk when you learn a word. Turn the array toward your chest and magnetocardiography. Let's cardiologists watch the heart's conduction pathways in patients where skin contact is risky or unreliable. Walk outside with a different geometry, gradiometers that cancel uniform background fields, and you can prospect for ore bodies and map buried faults by reading tiny changes in the ground's magnetization, or listen for the magnetic signatures of unexploded shells in a crowded harbor where ordinary metal detectors drown. In the lab, scanning SQUID microscopes hover a micron above a surface and turn the loop into a magnetic lens. They image the checkerboard of vortices in a superconductor, trace currents flowing along the edge of topological devices, and reveal nanoscale defects in integrated circuits by spotting the stray fields where a single via misbehaves. These instruments succeed because engineers treat the macroscopic phase not as a metaphor, but as a circuit quantity to be routed, shielded, and kept quiet. The loop is made small to reduce pickup of unwanted noise. The junctions are tailored to have the right current scale and damping. Multi-layer shields and cryogenic filters tame radio chatter, and clever patterns, washer loops, slotted shields, multi-turn pickup coils, improve coupling to the signals you care about while rejecting the ones you do not. There is a deep lesson in how noise is handled. The ultimate flaw isn't set by a sloppy amplifier, but by unavoidable fluctuations of the paired condensate and its environment. So the best SQUIDs approach an energy resolution close to fundamental bounds, and their outputs are then quietly escorted by cryogenic preamplifiers into room temperature electronics that can keep up without adding hiss. Because cooling used to be the price of admission, early systems lived in helium dewars that kept the SQUIDs at a few Kelvin while a patient or sample sat outside the cold window. But the last decade has delivered high-temperature versions that work with ceramic superconductors in simple cryocoolers and even wearable caps for brain mapping, shrinking the distance between sensor and source, sharpening spatial resolution, and opening doors to ambulatory studies that were science fiction when magnetically silent rooms were the only stage. The reach goes beyond imaging. SQUIDs anchor the quiet end of quantum electronics as preamplifiers for faint microwave signals from superconducting qubits, and as current comparators and voltage standards tied to fundamental constants. They keep metrology honest in a way no artifact object can. In particle and astrophysics, they sit behind cryogenic detectors that count single quanta of light from galaxy surveys or register minute heat pulses from potential dark matter interactions, their eyes pressed to the faint edge of what can be known. In geology, they read fields frozen into ancient rocks to reconstruct how Earth's magnetic poles wandered across eons. In materials research, they witness slow creep of vortices, map dissipationless edge channels, and verify that certain devices truly host currents immune to backscattering. None of this requires you to swallow mysticism. Every step is built from phase coherence, interference, feedback, and careful accounting. Yet the effect is still mind-bending. A device with no moving parts, a loop, and 2 slivers of barrier watches nerves fire inside a skull or follows a whisper of current around a micron-sized chip trace because a macroscopic quantum phase notices when its own angle shifts by a tiny fraction. If you want to see the philosophy in the hardware, notice how the instrument reverses the usual relationship between signal and sensor. Your sample does not push the SQUID into a new state by brute force, it merely nudges the phase a little, and the SQUID, being a disciplined interferometer, converts that nudge into a big, readable change with feedback doing the heavy lifting, just as a balanced scale makes a feather visible by comparing it to a known weight. There are hard edges too. A SQUID is so sensitive that stray magnetic grains, microvibrations, and thermal gradients can masquerade as signal, which is why shielded volts, vibration-damped tables, and meticulous cable routing matter as much as the physics. And there are creative twists that stretch what seeing means. Time division and frequency division multiplexing let thousands of SQUID eyes share the same wiring to build megapixel cameras for the millimeter sky, while hybrid sensors pair a SQUID with a mechanical resonator or a small magnet to translate forces and spins into flux, letting the phase see pressure, displacement, or even tiny nuclear magnetizations. By the time you step back, the device feels less like a detector and more like a language, the language of macroscopic quantum phase, written in loops and junctions that translates subtle, often living dynamics into voltages we can store, analyze, and act upon. And we can end gently with the thought that unites the engineering with the wonder. When we say macroscopic quantum phase, we mean that an everyday object, large enough to hold in your palm, is behaving like a single, coherent wave. And when we say SQUIDs as eyes, we mean that we have learned to aim that wave at the world and read its interference pattern as a picture. To build technology from that is not to domesticate mystery, but to work with it respectfully, letting coherence do what brute force cannot. And the next time you see a photo of a brain's magnetic rhythms or a map of vortices on a chip, remember that the camera was a loop that could tell when its own phase had shifted by an angle far smaller than a blink. And that is how human hands taught a piece of cold metal to see. Topological insulators. Protected edge highways. You expect an insulator to be dull and unhelpful, but here's a door that opens onto a stranger street map. Some crystals refuse to conduct in their interior, yet lay down perfectly paved highways along their boundaries, where electrons move with surprising immunity to bumps and detours. And once you see why those edge lanes exist, and why they're hard to sabotage, you start reading matter not only by what it's made of, but by how space is stitched together inside it. Begin with a two-dimensional sheet engineered so that its interior bands are separated by a clean gap, the textbook sign of an insulator, and now look to the edges, where the material meets air or another phase. Instead of the gap simply ending, special states appear that run along the boundary like guardrails, and their direction of motion is tied to an internal label, often the electron's spin, so that one spin races east while its partner races west, a pairing called spin-momentum locking. This is the essence of the quantum spin Hall effect in 2D and the seed of topological insulators more broadly. The bulk is quiet, the edge talks, and the rules that let the edge speak survive scratches, alloy disorder, and gentle bends because they are protected by a global property of the band structure, a topological invariant that cannot change without closing the interior gap. You don't need heavy math to feel the protection. Picture a narrow ledge skirting a cliff, with two one-way lanes separated by a wall of rules. An electron trying to reverse course would have to flip its spin and scatter into the opposite lane. But as long as the crystal respects time reversal symmetry, and you avoid magnetic spoilers, such backscattering is strongly suppressed, so the traffic keeps moving even when the ledge is rough. Scale up to 3 dimensions, and the story acquires a new face. The surface hosts massless, linearly dispersing states that trace a single cone in momentum space, a Dirac cone, and again the spin is locked perpendicular to the direction of motion, so a simple non-magnetic defect offers no easy way to send an electron backward. This is not hand-waving, but lab reality. Angle-resolved photoemission maps out the cone on materials like bismuth selenide and bismuth telluride. Scanning tunneling measurements struggle to find the usual standing wave patterns because the forbidden backscattering robs quasi-particles of their favorite echo, and transport devices see edge-dominated, non-local signals that persist after ordinary metallic paths are pinched off. The robustness has a precise boundary. bring in magnetic impurities, or lay a magnetic layer on top, and you break the symmetry that guarded the lanes. A gap opens in the surface states, and new physics arrives, sometimes in the form of a one-way, chiral edge mode at the boundary of the magnetized patch, a quantized Hall current that flows without an external magnetic field, the quantum anomalous Hall effect. The crucial insight to carry is that these boundary states don't exist because electrons like surfaces. They exist because the entire interior band structure is twisted in a way that cannot be untwisted locally. You can dent the crystal and strain it. You can sprinkle non-magnetic disorder and the edge lanes reroute, but refuse to terminate unless you force the bulk gap to close or break the protecting symmetry. That invariance gives designers a new category of levers. Instead of atom-by-atom precision, you target the right lattice structure, spin orbit strength and symmetry content, then let topology handle the roughness. There are many branches on this family tree, and they're worth distinguishing because they teach different habits. Time reversal protected topological insulators owe their highways to spin-orbit coupling and vanish under magnetization. Crystalline topological insulators protect their surface states with mirror or rotational symmetries, leading to faces that conduct while others do not. A geometric selectivity you can test by polishing different facets. Higher-order topological insulators push the idea further, hosting not surfaces, but sharp, one-dimensional channels along edges or even isolated corner states in 3 dimensions, reminding you that boundary can mean a hierarchy of boundaries. In the lab, creating a textbook example is both easier and harder than it sounds. Easy because the core phenomena are strong when chemistry gives you heavy elements and the right crystal fields. Hard because tiny amounts of unintentional doping turn the bulk slightly metallic and swamp the surface signal. So experimenters use gating, careful stoichiometry, or thin film growth to suppress interior conduction and let the boundary speak. Once tuned, the devices reveal telltale behaviors you can recognize without a microscope. Conductance that barely budges when you roughen the edge, weak anti-localization in magnetotransport reflecting spin momentum locking, and an unusual response when you attach ferromagnets or superconductors at the perimeter. Couple a topological edge to a conventional superconductor, and the induced pairing inherits the helical nature of the channel, opening routes to bound states at engineered defects that behave unlike any garden variety, quasi-particle, and that have attracted intense interest for fault-tolerant quantum logic, an ambitious goal that still demands honest engineering to tame disorder and temperature. But that follows a clean conceptual path. Turn to metrology and sensing, and you find that protected channels provide stable interferometers where phase is less easily scrambled, while in terahertz photonics, the same spin-orbit machinery that built the highways can be exploited to rectify or steer high-frequency currents at low power. A beautiful, if subtle frontier lies in how these materials couple electricity and magnetism. In certain magnetized topological insulators, the interior behaves like a medium with a quantized magnetoelectric response, an axion electrodynamics where an electric field can induce a precise magnetic polarization and vice versa, and recent thin film experiments have inched toward direct signatures of that coupling in carefully stacked layers. Even when you step away from electronics and think like a microscopist, the edge highways earn their keep as a probe. Scanning squids trace their flow around lithographed obstacles. Kerr microscopes catch time reversal breaking when you deliberately gap the surface, and nano-fabricated constrictions show quantized steps in conductance when individual modes are counted through a narrow channel. It's worth keeping a realistic eye on the limitations, because doing so strengthens the message. At room temperature, many topological materials still suffer from leaky bulks. The protection works best against non-magnetic disorder, but can be undermined by puddles of unintended magnetism, or by interactions that open alternate scattering routes, and practical interconnects must be patterned without accidentally shorting the surface to the bulk. Yet each of these challenges is a knob to turn. Improved crystal growth suppresses carriers, gating and heterostructures separate the surface channels from spurious paths, and engineered magnetic textures intentionally break symmetry to create chiral rails where you want them. The conceptual reward for you, the listener, is learning to flip your default question. Instead of asking, does this material conduct? You start asking, where does it conduct and what protects that conduction from being scrambled? And when the answer is at the boundary, protected by a global twist in the band structure, you know you've entered topological territory. Close softly with this change of eyesight. A topological insulator is ordinary in the middle and extraordinary at the edges. A lesson in how constraints written across an entire crystal can gift reliability where you need it. And as you imagine future circuits that shuttle information along lanes that won't easily backscatter, or sensors that keep phase intact against rough handling, you realize this isn't hype about exotic matter but a sober design principle. Use symmetry and topology to make the path itself carry the guarantee, so that what looks like an insulator at a glance becomes, where it meets the world, a highway laid by the mathematics of shape, inviting you to drive signals with less fear of getting lost. Fractional charge without fractional particles. You've grown up with the rule that charge comes in indivisible packets. The electron's unit is sacred, so here's a hook that seems to bend the rule without breaking it. In certain carefully arranged materials, you can measure pieces of that unit, neat fractions like a half or a third, not because nature secretly minted fractional electrons, but because the collective state of many ordinary electrons and a structured background allows charge to be portioned out in stable, countable shares. Begin with a one-dimensional chain whose bonds alternate strong and weak, a humble polymer architecture that prefers a dimerized pattern, and imagine flipping the pattern in the middle so the alternation is out of step on the left versus the right. At that join, a special pinned electronic state appears right in the energy gap, capable of holding half of a unit of charge relative to its surroundings. And if you probe sufficiently gently, you'll find that the soliton sitting at that domain wall behaves as if it carries charge 1/2, even though every constituent electron still carries the full quantum. The trick is that the missing half is not missing at all. It's smeared throughout the chain in a way controlled by symmetry and topology, so the localized defect borrows from the surrounding sea in such a disciplined way that any attempt to move or split it forces the whole pattern to change, keeping the fractional amount intact like a watermark. This is your first clean lesson in fractionalization without inventing new particles. The fraction is an emergent accounting property tied to the background order, not a property of an isolated object you could bottle, and its stability follows from the way the system's global pattern refuses to be continuously undone. Slide up to 2 dimensions, and the story acquires richer stages, where the background doesn't just dimerize. It winds in momentum space and then boundaries, steps, or magnetic textures can trap states that carry fractional boundary charge, their amount fixed by differences in polarization or by how the internal phase of the electron's wave functions twists across the defect. Here you meet a deep organizing idea. What fraction you measure is determined not by local chemistry but by a bulk quantity. The kind of topological invariant that neither alloy disorder nor gentle bends can change. So that an edge dislocation, a corner, or a narrow domain wall can hold a precise fraction that survives modest roughness and persists across samples. The spectacular cousin of this logic lives in high magnetic fields, where electrons condense into exquisitely correlated fluids, and the excitations act like anyone's, with fractionally quantized charge and memory of how they braid. But even there you don't need to posit fractional constituents. The electron remains whole, while the collective fluid's rules allow bundles of correlation to behave as if they carry 1/3 of a unit and to reveal themselves through telltale shot noise plateaus and step-by-step tunneling. Across narrow constrictions, if you're wary of hand-waving, think operationally. How would you catch a fraction in the act, gently enough not to smash it into ordinary pieces? One way is to count the tiny current fluctuations that occur when charges hop one by one through a narrow bottleneck. If the statistics line up with 1/3 of the electron's charge, they do not do so by accident. And another is to park a sensitive electrometer, such as a capacitively coupled island or a scanning single electron transistor, near a domain wall engineered to host a fractional bound state, and watch the offset in its charging steps shift by a half when the defect is present. Crucially, none of these observations require you to break the fundamental unit in the vacuum sense. Take the material away, and you cannot keep the fraction in a jar, because the background order you leaned on has vanished. and with it the accounting scheme that made the fraction meaningful. This view clears up a common confusion. How can an electrical measurement claim half a unit when all currents are carried by whole electrons? By separating instantaneous motion from long-term bookkeeping. Locally, currents still come in discrete electron events, but the background polarization and the mid-gap states they support redistribute where the electron's responsibility for charge begins and ends, so the device's integrated response assigns a fraction to the defect. With the same authority it assigns a whole unit to an isolated donor. It also teaches you what can kill the effect and what cannot. Non-magnetic disorder may blur shapes, but cannot change the allowed fraction as long as the protective symmetries and the energy gap survive. While strong symmetry breaking, say, adding magnetic impurities when time reversal protection was your shield, or driving the system through a transition that closes the gap, can erase the conditions that made fractionalization robust. Engineers have begun to treat these fractions as design elements rather than curiosities. Molecular chains and artificial lattices are patterned to host domain walls where half charges can be toggled by gates. Metamaterials are sculpted so that corners accumulate quarter charges determined by the crystal's rotational symmetries, and hybrid devices couple a fractional bound state to superconducting circuits, letting the presence or absence of that fraction tip a quantum interference loop and serve as a low-power, non-volatile bit. The same mindset shows up in one-dimensional conductors, where injecting a single electron doesn't travel as a single packet at all, but splits into separate pulses that carry different parts of the electron's identity, its total charge and its internal spin. And while that's a different kind of fractionalization, born of interactions rather than topology, it underscores the larger lesson. The unit you learned in freshman physics is not violated, but re-expressed when many body coherence and symmetry fence in what counts as a distinct movable object. If you're looking for a quick test to separate credible claims from hype, carry this checklist. The fraction must be tied to a gap and a protecting principle so that it survives moderate disorder. The signal should show up in integrative probes, offsets in Coulomb steps, quantized slopes in polarization measurements, plateaus in noise or tunneling exponents, rather than in pictures that could be explained by stray doping. And the effect must turn off when you deliberately break the protection, either by closing the gap or by flipping the relevant symmetry, because a robust fraction without a controlling rule is a red flag. The conceptual payoff of seeing fractions correctly is large. It frees you from the false dichotomy between fundamental and illusory, and teaches you to ask what the background makes possible, how defects inherit charge from polarization differences, how edges and corners can carry responsibilities the bulk refuses, and how carefully arranged interactions can make the electron's influence arrive in pieces, even as the electron remains itself. It also nudges you to read devices differently. Instead of thinking only in terms of carriers moving through channels, you begin to think in terms of bound charges assigned by topology, of domain architecture as an address book for where charge can live, and of measurement as an exercise in patient, system-level accounting. So we end with a gentle reframing that will serve you in the rest of this series. Fractional charge in solid-state systems is not a loophole in nature's rules, but a lesson in how rules at one level, symmetry, topology, and many-body coherence, decide what can be packaged and handed around at the next. And when you learn to design those backgrounds, you can make halves and thirds appear without ever breaking the indivisible, turning what seems like a paradox into a tool that measures cleanly, stores information quietly, and deepens your sense of how the same electron can write very different stories depending on the stage it plays on. Anyone's braiding as identity. You're used to the idea that swapping two identical things changes nothing. Two marbles trade places and the world shrugs. So here's a doorway where that intuition fails in a precise, useful way. In certain two-dimensional quantum systems, exchanging identical excitations can imprint a memory on the system, a global twist that doesn't wash away when the particles settle. And those excitations are called anyones, because their behavior can be anywhere between the familiar extremes. Begin by anchoring the contrast. Bosons and fermions are defined by how a system's quantum state responds when you trade two of them. one leaves the state unchanged, the other flips its sign, and neither option is something you can dial. But in flat, strongly correlated matter, the collective wave function can track not just that a swap occurred, but how the paths wrapped around each other. So a neat repeatable phase enters that is neither zero nor a simple sign. And now exchanging twice is not the same as not exchanging at all, because the path you took matters. That is the abelian story, where each swap multiplies the state by a fixed phase that stacks additively. But the deeper shock is the non-abelian case, where swapping is more like twisting a Rubik's cube. The state is gently rotated within a multi-dimensional space of possibilities, and the order in which you braid two pairs matters, because doing left then right does not land you in the same place as right then left. This sensitivity to braiding is not decoration, it is identity. You cannot fully specify what kind of anyones you have, nor what joint state they occupy, without listing how they got there, which braids were performed, and how they were fused in the past. So history becomes part of the label. If you want a concrete stage where this strange bookkeeping is real, go to the extreme edges of the fractional quantum Hall effect, where clean two-dimensional electron gases cooled and placed in strong magnetic fields, organize into correlated fluids that host excitations carrying fractional charge, and crucially, obey exotic exchange rules. There the edge of the sample acts as a waveguide for current, and small constrictions function like beam splitters for those excitations, letting experimentalists build interferometers that test whether going around a loop picks up a phase tied to how many anyons sit inside. When the loop encloses an extra fractional excitation, the interference fringes shift by a telltale amount, an electrical fingerprint of abelian braiding, and when gates or magnetic fields are swept, the conductance oscillates with a periodicity that cannot be explained by ordinary electrons making the trip. Push to certain rare filling conditions and theory predicts non-abelian anyons. Add or remove one of these defects and you don't just shift a phase, you change the dimension of the hidden state space, and braiding different pairs becomes a sequence of operations you can string together like moves in a language. In parallel, solid-state engineers have built one-dimensional nanowires with strong spin-orbit coupling and proximity to a superconductor, then applied magnetic fields to open a topological gap and trap zero-energy modes at the ends, Majorana-bound states that behave like half-quasi-particles. Bring two ends together and you recover an ordinary fermion. Keep them apart and exchanging their endpoints ought to perform a non-abelian operation on the joint quantum state. The promise here is both philosophical and practical. If the only way to scramble the information stored in such a system is to physically braid the anyons out of order or to close the energy gap protecting them, then local noise, atoms jittering, fields wandering, electrons colliding, falls short and your quantum memory can ride above the mess like a raft over chop. This is the North Star of topological quantum computation. Choose a platform whose excitations are non-abelian, encode qubits in the presence and pairing of these excitations, and compute by braiding them along planned paths. The gates are world lines weaving in time, and errors that don't alter the braid don't alter the computation, a kind of hardware-level error correction gifted by the system's global constraints. To see why the label braiding as identity is earned, think about fusion rules, the ways anyons can combine. Two of the simplest kind may merge to make either a neutral vacuum or a different anyon, and which outcome you get depends on the collective state, not on a secret internal tag glued to each one. This means counting anyons is not counting particles, but counting possible joint states, and braiding nudges you from one allowed superposition to another. Non-abelian platforms come with their own suite of experimental signatures, tunneling conductance that reveals a zero bias peak consistent with a protected mode at a wire's end, teleportation-like parity correlations between distant ends, and thermal conductance along edges that counts the effective number of moving modes even when electric conductance is muted. None of these signatures alone is a proof, because disorder, unintended ordinary states, and coherent but non-topological tricks can fake parts of the story, which is why the community insists on cross-checks, interferometry that responds to enclosed topological charge rather than to small shifts in area, fusion rules tested by controlled creation and annihilation of excitations in pairs, and braids executed in different orders to verify that the results refuse to commute. What you should carry into your own reasoning is that anyones are not third kinds of particles waiting out in the vacuum. They are emergent actors, born from the global organization of electrons in particular phases of matter, and outside those stages they do not exist. Their strange accounting is a property of the whole system, encoded in a gap that insulates the low-energy sector from the rest, and in symmetries that keep the rules from unraveling as you nudge or dirty the sample. That perspective clarifies what can break them. Close the gap by heating, doping, or applying the wrong fields, and the protected subspace spills into the noisy continuum. Break the symmetries that the phase needs, and paths that were once distinguishable by their winding blur together, but also what cannot easily break them. Non-magnetic impurities, small bumps at the edges, or modest deformations, all of which reroute currents and shift phases, but leave the topological backbone intact. This balance between fragility and resilience is why anyone's are compelling for metrology too. You can build sensors whose response depends on whether a loop encircles an anyone, a topological on-off switch that resists ordinary drift, or design current standards that count tunneled charges in unusual fractions, with noise plateaus that calibrate themselves. If you want a mental model without equations, imagine a thin dance floor tiled with arrows that must align to certain local rules. Most steps are forgettable, but when two dancers weave around each other in a particular pattern, the entire floor shifts to a new choreographic state that can be recognized by watching the edges long after the dancers have parted. Do the moves in the opposite order, and the ending tableau is different, even though each move looked the same to a nearby observer. You cannot diagnose what happened by examining one footfall. You must consult the entire braid, closing gently. This is the habit anyone's teach. In some corners of physics, identity is not what an object is, but what has been done with it. Not a tag, but a trace. Once you accept that, you see why two dimensions matter, why gaps and symmetries are precious, and why a future quantum computer may look less like a rack of humming processors and more like a quiet plate where a few bright dots are braided with care, each loop of their dance writing an operation that no amount of local fuss can easily erase, turning history itself into a resource. Magnons, Phonons, Polaritons, Plasmons explained. You might think vibrations, spins and light are background actors in solid matter, but here's a cleaner way to see the cast. Many of the signals we measure in crystals and thin films are best described not as individual particles flying around, but as quantized ripples of whole communities moving in step. And learning their names, Phonons, Magnons, Polaritons, Plasmons, turns a noisy world into a readable score. Start with Phonons because they are the most tangible. Imagine every atom in a crystal joined to its neighbors by springs that can stretch and compress. And when the lattice pulses collectively, those motions come in organized patterns, some where neighboring atoms move together, others where neighbors move opposite. And each pattern can carry a tiny, countable packet of vibrational energy called a phonon. You meet phonons every time heat flows through a solid, because at room temperature, most thermal energy in an insulator is stored as these lattice ripples, and the way they scatter, off impurities, off each other, off the edges of a device, sets the thermal conductivity that engineers fight or exploit in microchips, LEDs, and thermoelectrics. You can watch phonons directly. In Raman and infrared spectroscopy, a laser probes specific vibrational fingerprints like a stethoscope on a crystal's chest, while neutron scattering maps their speeds and lifetimes across momentum space, revealing which pathways carry heat and which die young. Temperature modifies this chorus in systematic ways. At high temperatures, the ripples collide more often and heat transport falls. At low temperatures, the mean free path can stretch to millimeters and heat moves ballistically like a beam, and careful isotope substitution even shifts the vibrational pitches, a trick material scientists use to tune thermal and optical properties without changing the chemistry. Now turn from motion of atoms to motion of spins and you meet magnons, the quanta of spin waves. In a ferromagnet, the microscopic magnetic moments prefer to align, but they can ripple collectively so that the direction of alignment twists gently from place to place. And a single quantum of that wave is a magnon, Unlike a stray electron that bounces off defects and loses memory quickly, a long wavelength magnon can travel comparatively far inside a clean magnetic crystal, carrying angular momentum without charge, which is the door into magnonics and spintronics, fields that aim to route information using spin waves for lower dissipation than ordinary current. Real measurements make magnons vivid. Inelastic neutron scattering draws their dispersion map, showing how their energy depends on wavelength. Brillouin light scattering counts them one by one with a laser at the surface. And the spin-Seebeck effect shows that a mere temperature gradient can pump a magnon flow detectable as a voltage in an adjacent metal, opening ways to build logic elements and oscillators that consume less power and generate less heat. Shift your attention to hybrids, and a new actor appears. The Polariton, a light matter duet where a photon inside a resonator or near a surface locks to a material excitation, and the pair propagates as a single entity. Depending on the partner, you get different flavors. Phonon polaritons form when infrared light binds to a polar lattice vibration and can squeeze energy into volumes smaller than its free space wavelength, letting you route and focus mid-infrared light in crystals like silicon carbide with nanometer precision. Exciton polaritons arise when light couples to bound electron-hole pairs in semiconductors and can form macroscopic quantum states at surprisingly high temperatures compared to cold atom systems, which is why microcavity devices made from gallium nitride or organic films can show lasers with ultra-low thresholds and even condensation-like behavior of these hybrid quanta. Surface plasmon polaritons live where light binds to collective electron motion at a metal interface, guiding optical energy along a surface rather than through space and enabling waveguides, switches and sensors that beat the usual diffraction limit. To see the hybrid character is to notice two clean signatures. First, the spectrum splits into two branches when coupling is strong, the hallmark of shared identity, and second, the resulting waves can be steered by both photonic design and material design, giving engineers two sets of knobs to tune. Finally, meet plasmons themselves, which are not hybrids, but pure collective oscillations of a sea of electrons sliding against the positive background in a metal or doped semiconductor, as if the whole electronic fluid rocked back and forth in a dish. Squeeze that fluid into a nanoparticle and the oscillation becomes a localized surface plasmon, which concentrates electric fields into nanoscopic hotspots and is responsible for the bright, tunable colors of metallic nanostructures. Think medieval stained glass that looked magical long before we learned it was nanoscale metal at work. Modern devices exploit this concentrated field to boost weak signals. Surface-enhanced Raman spectroscopy reads the vibrational fingerprints of single molecules sitting in those hotspots. Hot carrier devices harvest energetic electrons created as the plasmon decays, and near-field microscopes use metallic tips to pull sub-wavelength detail into view by hitching a ride on plasmonic confinement. In two-dimensional materials like graphene, plasmons can be pushed to astonishingly short wavelengths and tuned by a simple gate voltage, allowing mid-infrared and terahertz waves to be trapped, steered, and switched on chips thinner than a flake of paint. Across all four actors, the unifying idea is that particle is an efficient label for a collective pattern with a life of its own. Phonons carry heat and sound through ordered motion of atoms. Magnons carry spin information through ordered twists of magnetization. Plasmons carry charge density waves through the electronic fluid. And polaritons carry mixed identities that inherit features from both light and matter. The payoff of naming them isn't vocabulary pride, it's control. Once you know which quanta dominate a property, you can design to help or hinder them. Roughen a surface or add nanoscale pillars to scatter phonons and keep heat in a thermoelectric. Polish and purify to let phonons fly when you want a heat spreader. Pattern magnetic films to shape magnon paths and build phase-based logic. Build cavities and gratings that place polaritons where you want them for low-power light sources or detectors. Sculpt nanoparticles and choose metals or doped semiconductors that set plasmon frequencies for sensing, imaging, or energy conversion. And always measure with the right ears: neutrons for magnons and high-energy phonons, light for Raman active phonons and Brillouin modes, ultra-fast pump probe techniques for polariton dynamics, electron energy loss spectroscopy for plasmons. You don't need equations to hold the final picture. These quanta are the currencies in which solids pay their debts and store their wealth. Heat, magnetism, light, and charge. And understanding their roots and exchange rates lets you write cleaner contracts between materials and functions. So the next time a device runs hot, a sensor reaches past the diffraction limit, or a memory element switches with a whisper of energy, you'll know which collective actor made it possible, and you'll start seeing matter not as a static backdrop, but as an orchestra in which different sections carry different themes, ready to be quieted, amplified, or coupled into harmonies we can use. Quasi-particles, real enough to measure. You've been told that matter is made of particles, so here's a sharper lens that will change how you read experiments. In crowded, interacting systems, the useful things aren't always the original electrons or atoms, but dressed disturbances that move as if they were particles, quasi-particles, abstractions that become real the moment you ask a measuring device what passed by. Begin with a simple metal cooled so that thermal smearing is small, and picture an electron trying to travel through the sea of its peers. It tugs on nearby charges, stirs gentle density ripples, borrows inertia from the crowd, and, after all those negotiations, emerges as a composite traveler with a modified mass, a finite lifetime, and a strength of identity you can quantify. This dressed electron is not wishful thinking. It leaves fingerprints you can collect. Angle-resolved photoemission draws a direct image of energy versus momentum and shows a sharp peak, the quasi-particle, whose slope gives the renormalized velocity and whose width gives the inverse lifetime, while the remaining haze in the spectrum is the background many-body chatter the particle carries in its wake. In clean crystals exposed to strong magnetic fields, the same entity writes oscillations into magnetization and resistance, from which you extract cyclotron mass and infer the size and shape of the Fermi surface, geometry that belongs not to bare electrons, but to their dressed counterparts. In the time domain, an ultra-fast pump probe experiment can shove a packet of these travelers out of equilibrium, and a delayed probe watches them relax, their decay curve reporting how robust the quasi-particle picture is, and which scatterers, impurities, lattice vibrations, or other electrons set the tempo. Now widen the cast beyond metals and you meet other, equally measurable actors born from interaction. Add an electron to a polar crystal and it drags a cloud of lattice distortion, becoming a polaron whose mass and mobility are not the electrons alone. Shine light on a semiconductor and you create excitons, bound electron hole pairs, that wander like neutral particles with their own spectra and lifetimes visible in absorption and photoluminescence. Drive a superfluid ever so gently, and its sound-like mode behaves as a bona fide quasi-particle that carries momentum and energy with a well-defined dispersion you can map by neutron or Brillouin scattering. In magnets, the soft torsions of alignment appear as spin waves, and their quanta, Magnons, propagate information without charge, giving you non-volatile signals that can be launched and detected with microwave antennas and read out as clear peaks in scattering experiments. The thread connecting these examples is operational. A quasi-particle is whatever produces a sharp, controllable response with stable parameters over the times and distances you care about. And sharp has a precise meaning. Its spectral peak is narrow compared to its energy, so it carries identity long enough to be used as a carrier of heat, charge, spin, or light. This practical stance answers a common worry with a lab bench retort. Bookkeeping that predicts concrete, falsifiable numbers, effective masses from quantum oscillations, heat capacities that scale with those masses, scattering rates that track known interactions. Quantized steps in transport when modes are counted one by one is not decoration, but the very language of control. The same stance also tells you when to abandon the concept. If your spectra lose sharp peaks and smear into broad continua, if relaxation becomes as fast as the oscillation itself, the object you tried to name doesn't survive long enough to be useful, and you must change descriptions to collective hydrodynamics, incoherent transport, or scale-free responses. You don't need dense mathematics to feel how the parameters of a quasi-particle are minted by the medium. The effective mass is a measure of how much surrounding stuff must be nudged when the disturbance moves. The lifetime is the average distance it can go before the crowd reabsorbs it. And the quasi-particle weight, the fraction of the spectral response carried by the sharp peak, tells you how much of the original identity remains after dressing. By measuring these three numbers across temperature, pressure, and doping, researchers map where the particle picture holds and where it frays, which is why phase diagrams in modern materials science are annotated not only with ordered states, but with regions labeled coherent or incoherent, a shorthand for the survival of quasi-particles. Devices translate these abstractions into engineering. In high-mobility transistors, long-lived charge quasi-particles deliver blistering speeds. In thermoelectrics, you intentionally shorten phonon quasi-particle paths while preserving electronic ones to break the usual link between electrical and thermal conductivity. In magnetic memories, carefully engineered Magnons carry signals over microns with microwatts, a bargain impossible with hot electron currents. In nanophotonics, exciton resonances sharpen light-matter interactions so much that a handful of quantum emitters can control a cavity's response, while in detectors for astronomy and quantum sensing, a single quasi-particle breaking a superconducting pair becomes a countable event that registers as a clean pulse. Measuring real enough also means minding the interfaces where quasi-particles can convert from one type to another. An energetic electron entering a polar crystal will quickly shed energy by making optical phonons, a cascade you can watch with ultra-fast methods. A spin-polarized current dumped into a magnetic insulator launches a burst of Magnons, whose existence is confirmed by the voltage they induce in a neighboring strip via spin pumping. A vibrating nanobeam coupled to a microwave cavity trades phonons for microwave photons one by one, letting you move information between mechanical and electrical domains with single quantum precision. Each conversion comes with selection rules and efficiencies that you can redesign by controlling geometry and purity, knobs that exist precisely because the quasi-particles have stable identities. Yet the humility clause matters. No renormalized mass or lifetime is carved in stone. Change the background, and you change the traveler, which is why the same chemical element can act wildly differently in two compounds. Dressed by one lattice, it becomes a heavy, sluggish carrier. Dressed by another, it remains nimble, and why the same material can cross from a regime where the particle picture rules to one where it fails as you dial a non-thermal parameter. This plasticity is a feature, not a bug, because it hands you a playbook to make carriers fast, reduce the channels that let them dump momentum. To carry spin far, tailor the spectrum of magnetic excitations so Magnons live long. To route light below the diffraction limit, couple it to a long-lived hybrid mode with a narrow line width. And to detect single quanta, design an absorber where one broken pair or one trapped exciton precipitates an avalanche you can read above noise. The final habit to keep is epistemic discipline. Call something a quasi-particle only when you can point to the measurement that reveals it. A dispersion with a clear line, an oscillation with a clean period, a peak whose width shrinks as the system quiets. And be ready to retire the label where those signatures fade. Closing gently, this is the lesson that steadies your thinking across complex matter. Real in physics means makes reliable, quantitative appearances in instruments, and by that standard, quasi-particles earn their names every day, sometimes long-lived enough to underpin technologies, sometimes fleeting but still diagnostic of the forces at play, and learning to see them, count them, and, when needed, let them go is how you turn interacting many-body chaos into a library of usable actors, each real enough to measure, real enough to design with, and honest enough to disappear when the medium that sustained it changes its mind. Quantum pressure stabilizing stars, you expect gravity to be the final word in the lives of stars. A steady pull, with no mercy once the fuel runs out. So let's enter the quieter, truth that saves entire suns from complete collapse. When nuclear fire fades, a purely quantum push can hold matter up, not because heat props it like a balloon, but because the basic rules for identical particles leave no room for them to be squeezed arbitrarily close. And that resistance, quantum pressure, stabilizes dead stars in ways you can measure from Earth. Begin with the Pauli principle stripped to its essence. Electrons are indistinguishable and cannot share the exact same state. So as you compress matter and fill the lowest available slots, additional electrons are forced into higher momenta, which means even at zero temperature, There is an irreducible jostle that registers as pressure. This is not gas pressure in the everyday sense. It is degeneracy pressure, a flaw that rises with density because more states are crammed into a smaller volume, and when a star like our Sun exhausts its core fuel and shakes off its outer layers, the leftover core cools into a white dwarf balanced precisely by that electron degeneracy against gravity's squeeze. The predictions are crisp and strange in just the right way to trust them. For white dwarfs, the more mass you add, the smaller the star becomes, because the added gravity drives the electrons to higher momenta, stiffening the quantum pressure and forcing the object to a tighter equilibrium, an inverse mass-radius trend confirmed by measurements of objects like Sirius B and companions in binary systems, where mass and size can be pinned down independently. Push the mass still higher, and relativity starts to matter in a new way, not just in gravity's pull, but in how the electron's momenta approach light speed, softening the support until a threshold appears, the famous limit above which no amount of electron degeneracy can hold the star up. Cross that boundary, and the white dwarf cannot find a stable radius. Its electrons get captured by protons, neutronizing the matter and triggering collapse. If the mass of the collapsing core is modest, the story can stabilize one rung deeper into quantum rules, because now neutrons, also indistinguishable, take over the role of the resisting crowd. And neutron degeneracy plus short-range repulsion between neutrons grind gravity to a halt at radii of about 12 kilometers, building a neutron star whose density climbs past that of atomic nuclei. Again, the counterintuitive signature is measurable. These stars are absurdly small for their mass and precision timing of pulsars. The lighthouses formed when magnetic neutron stars spin yields masses around 1 and even 2 times that of the Sun, while other observations constrain their radii, painting a narrow band in the mass-radius plane that any viable model of their internal pressure must pass through. The logic deepens because not all quantum pressure is the same stiffness. In white dwarfs, the equation of state is fairly well understood from a sea of electrons embedded in a lattice of nuclei, and even includes crisp phenomena like crystallization as the star slowly cools, its interior literally forming a solid lattice that changes how it cools and dims. In neutron stars, the situation becomes a research frontier, because at a few times nuclear density, new degrees of freedom may open. Hyperons, meson condensates, or even deconfined quark matter could soften or stiffen the pressure, and the way the star's radius and maximum mass respond acts as a Rosetta Stone for dense matter physics. Nature has already handed us anchor points. Several pulsars weigh in above 2 solar masses, which rules out overly soft equations of state that would crumble under such load. While X-ray pulse profile modeling and gravitational wave measurements from neutron star mergers have started to box in the typical radius and the tidal squishiness, tests that treat entire stars as laboratories you cannot build on Earth. The practical clues are delightfully diverse. When 2 neutron stars spiral together and merge, the gravitational wave signal encodes how deformable the stars were, and if a hypermassive remnant briefly survives before collapsing to a black hole, the timing and electromagnetic afterglow tell you how stiff the interior had been. In quieter systems, delays induced by a companion's gravity on pulsed radio beams, or sudden glitches as a star's crust repins to its superfluid interior, reveal a body made of layers whose responses are set by quantum mechanics rather than chemistry. At the lighter end of cosmic objects, the same degeneracy logic explains why brown dwarfs, failed stars that never ignite sustained hydrogen fusion, maintain similar sizes over a wide mass range. Electrons inside them are partially degenerate, so adding mass doesn't puff them up, and in gas giants like Jupiter, the compressibility of the deep interior already hints that electron degeneracy has joined the balance sheet. All of this reshapes how you think about stability. Thermal pressure is negotiable. It fades as a star cools, whereas the quantum floor is not, and you can't siphon it off or trade it for work because it isn't stored heat. It is a structural consequence of the allowed states for the particles involved, a bookkeeping rule that becomes a force when gravity insists on crowding. The sky's inventory then sorts cleanly. Below a certain mass, stellar corpses live as white dwarfs. Push core masses past that, and you land on neutron stars. Push further still, beyond the neutron star's maximum mass, and even neutron degeneracy plus nuclear repulsion yield, the object collapses into a black hole where no known microphysics can halt the fall. The thresholds are not trivia. They control which supernovae leave behind, which remnants, how heavy elements are forged, and how galaxies enrich themselves with the ashes of prior generations. There is a philosophical payoff too. Pressure here is not molecules bouncing, but a refusal written into the quantum identity of matter. No two identical fermions may stack into the same state. And when gravity asks for tighter packing, the answer becomes an outward force. That answer is measurable in ways that would be impossible if this were mere metaphor. It sets star sizes, cooling curves, oscillation modes, and maximum spins. It creates phenomena like the white dwarf's crystallizing heart and the neutron star's superfluid interior, whose vortices creep catastrophically to produce sudden spin-ups. It even explains why the least massive white dwarfs are larger and the most massive are smaller, a relation so odd that it served as a diagnostic long before the microphysics was settled. Keep a sober eye on limits. Quantum pressure is not a license for perpetual support against any load, nor is it an energy source to be mined. At each rung, new physics enters and sets a ceiling, above which collapse is inevitable, and the universe uses those ceilings to sort its remnants. Yet within those limits, the quantum rules keep literal suns from becoming singularities, building quiet endpoints that are stable for billions of years. If you cultivate one habit from this story, let it be to ask, whenever you meet an extreme object, what sets its flaw? Is it heat, rotation, magnetic tension, or the Pauli principle? And then to read the object's measured properties as answers to that question. End gently with the image that best fits the evidence. Gravity writes the overarching plot for stars, but when the fuel is gone and the curtain should fall, quantum mechanics steps from the wings and holds the stage, sometimes at Earth size, sometimes at city size, long enough for us to time their pulses, chart their masses and radii, and learn from their steadiness that even in a universe ruled by collapse, there exist quiet forms of support that are not about pushing back loudly, but about refusing, at the deepest level, to share the same state. Vacuum as a dielectric, screening intuition. You grow up thinking only matter can muffle electric fields, that glass, water, or ceramic screen a charge, while empty space just watches. So here's a gentler and truer picture to carry forward. Even the vacuum behaves like a dielectric, a medium that can be polarized, and when you place a charge in it, the surrounding quantum fields subtly rearrange so that what you feel at a distance is not the raw source, but a dressed version, softened by a halo you cannot see yet can measure. Begin with a memory from everyday dielectrics. Put a charge near a piece of plastic, and the plastic's tiny dipoles tilt, reducing the field that leaks through. And now scale that idea down until the dipoles are not molecules, but fleeting ripples of the electromagnetic field itself, briefly correlated pairs that the field can stir into alignment, and those ripples are tugged by your source in such a way that positive wiggles spend a little more time on one side and negative wiggles linger on the other, creating a polarization cloud that partially cancels the field, which means that the electric charge you infer from far away is slightly smaller than the bare one you'd infer up close. This is not a parlor story, but the backbone of precision physics, when experimenters probe the strength of electromagnetic interactions at higher and higher energies by smashing particles together or measuring how much they deflect. They consistently find that the effective charge grows as you push closer, a sign that you've outrun part of the screening haze and are interrogating the source more directly. And the same vacuum as medium logic leaves small but specific fingerprints on atomic energy levels and on the exact probability that light briefly morphs into charge pairs and back as it threads a heavy nucleus. None of this requires you to imagine literal particles popping in and out like gnats. What fluctuates is the field, and pairs are our shorthand for how the field's charge components contribute to polarization. But the accounting is rigid. Fields with electric charge add to screening and make the long-distance force look a touch weaker, while neutral fields sit quietly. You can test this picture in multiple orthogonal ways. Count how the effective coupling changes when new kinds of charged matter are energetic enough to join the dance. Compare scattering data taken at very different momentum transfers and watch the same law of force bend by a calculable amount. Or examine how the probability of creating certain final states shifts as you dial the probing scale. What you're really learning to read is the running of interaction strength with scale, reframing the electric charge as a number that belongs to a measurement context, not a platonic constant engraved on the electron's skin. And that humility pays off because it explains why the fine structure constant quoted by atomic spectroscopists is not the same value accelerator physicists use when calculating collision rates on the Z boson peak. The vacuum's polarization has a scale, and your instrument decides which slice you sample. This dielectric view also clarifies the difference between static quiet and violent fields. In moderate settings, the vacuum's polarization is a reversible tilt that returns to baseline when you remove the source. But if you crank the electric field toward the extreme, the medium can break down in a quantum sense, turning enough field energy into real charged pairs that the field drains itself. So even empty space has a notional breakdown field, unimaginably high by laboratory standards, yet conceptually the same kind of threshold that decides when a real dielectric starts to spark. There's a subtle twist worth holding on to. The vacuum does not screen every force the same way, and this contrast sharpens your intuition rather than dulls it. Electromagnetism gets softer at long distance because its vacuum polarization points against the source, but the strong interaction governed by a different symmetry does the opposite. Its vacuum behaves more like an anti-dielectric, so that color charge becomes weaker as you push closer. A reminder that vacuum as medium is a general principle with force-specific personalities. The practical payoffs are not hidden in exotic corners. They are how we calibrate reality. We fold vacuum polarization into the values printed on reference charts. We include it when we compute magnetic moments of electrons and muons, or the slight bending of light near heavy elements. And we design experiments to isolate its contribution by subtracting every classical effect we can name. In that daily work, you can watch a simple mental image become quantitative, just as a material dielectric can be summarized by a number that says how easily its dipoles tilt. The quantum vacuum's ease of polarization is encoded in calculable functions that depend on scale, and those functions tell you how much the electric field lines are pinched inward by the cloud as you change distance, how strongly the cloud responds near the threshold to create real pairs, and how new species of charged fields, when the energy lets them participate, make the screening thicker. There are edges to respect so you don't confuse metaphors with mechanisms. The vacuum's polarization is not heat and cannot be harvested. It is not a reservoir you can pump for work. And it does not imply that the electron is a fuzzy object you can slice into pieces. Rather, it says that any attempt to separate the source from its surroundings is artificial, because the field that defines the source also defines the medium it lives in. That recognition gives you cleaner language for thorny questions. What is the true charge? What does it mean to renormalize? Why do some infinities disappear when you compare measurements at two scales? And the calm answer is that we choose a reference scale to define our units. We calculate how the vacuum's response shifts that definition as we move away from the reference. And we always compare like with like when we test theory. Bring this back to your hands and instruments, and it stops being an abstraction. A high-energy collider reading a slightly larger interaction probability at small distances, an atomic clock ticking at a rate that depends on levels nudged by polarization near a nucleus, a detector's electronics calibrated to a constant that theory tells you should be evaluated at the frequencies that dominate your signal. These are all unromantic ways the dielectric vacuum shows up, and yet there is room for a soft closing thought. Because this story invites a small change in how you imagine emptiness. Instead of a passive absence, picture a disciplined backdrop with a willingness to lean, a medium that respects conservation and causality, while still sharing some of the character we assign to matter, susceptibility, response, memory of scale, and once you carry that image, the world's forces feel less like edicts delivered across a void, and more like conversations conducted through a transparent fabric. One that can be slightly stretched and ever so slightly relaxed by the very charges you bring into it. In that fabric, screening is not the universe hiding the truth of a source, but the universe telling you that truth depends on how closely you listen, and the better you tune the distance and the energy, the more honestly the vacuum will show you the charge it has been holding all along. Entanglement spectra as phase fingerprints. You're used to recognizing phases of matter by what your eyes can see: crystal patterns, magnetization arrows, edge currents. So here's a quieter test that works even when the sample looks featureless. Slice the quantum state in your mind, listen to how the two halves remain entangled, and read the entanglement spectrum as a fingerprint that reveals which phase you're in. Begin by picturing a many-body ground state that you divide into region A and region B, not with a knife, but with an imaginary boundary, and then ask a simple question. If you could only access A, which patterns of A would you find likely, and how strongly are they weighted once you've forgotten B? Mathematically, that inventory of likelihoods is the set of eigenvalues of A's reduced state, but you don't need the algebra to feel the idea. The entanglement spectrum is the histogram of how A tends to be when coupled to B, and miraculously, that histogram carries universal structure tied to the phase, the way a song's chord progression tells you the genre even before the melody arrives. This is not a poetic stretch. It's a workhorse diagnostic born from a deep edge-bulk correspondence. In wide classes of gapped systems, the low-lying part of the entanglement spectrum for a clean cut looks like the actual spectrum of a physical edge living at that cut. So if your phase would host protected edge modes, say, counter-propagating spin-filtered channels or a chiral track that runs one way, those modes reappear as characteristic level counts and spacings in the entanglement spectrum, even though your sample has no literal boundary. That's why topological phases that hide their order from any local snapshot, integer and fractional quantum Hall fluids, time reversal protected insulators, topological superconductors, and spin chains with symmetry protected order announce themselves through distinctive entanglement fingerprints, a specific degeneracy pattern that refuses to split as long as the protecting symmetry is kept, a ladder of levels whose counting matches the conformal field theory describing the edge, or a clean entanglement gap that stays open within a phase and pinches shut at a transition. You can see the power of this test in concrete examples. The ground state of a spin 1 chain in its hidden ordered phase shows pairs of nearly degenerate entanglement levels, reflecting effective spin. 1-2 edge states that are invisible in the bulk magnetization. Numerical ground states of fractional quantum Hall systems, when cut along a circle, present an entanglement spectrum whose low energy level counting mirrors the known chiral edge theory and even distinguishes different filling fractions that share similar transport. Two-dimensional churn insulators, which can look mundane in real space density, produce a flowing entanglement band that crosses from filled to empty as momentum along the cut is swept, mimicking the single robust edge mode you would measure with a probe, and symmetry-protected phases beyond simple magnets. Crystalline topological insulators, for instance, display entanglement spectra whose stability depends on the same mirror or rotational symmetries that protect their surface states, telegraphing which faces will conduct before you polish a single facet. The method scales beyond pretty pictures because it respects universality. As you tune a Hamiltonian across a quantum phase transition, the entanglement spectrum usually tells you before other observables do. The entanglement gap shrinks and new sequences of levels invade, long before finite size order parameters settle. At the same time, it's a scalpel rather than a sledgehammer. Two models can share similar correlation functions, yet fall into distinct topological classes that the entanglement spectrum separates cleanly, because it is sensitive not only to how far correlations reach, but to how quantum information is organized across the cut. You might worry this is a purely numerical toy, but the bridge to experiment is tightening. Cold atom platforms already measure coarse entanglement properties by interfering two identical copies of a state to extract Renyi entropies, and refined, randomized measurement protocols reconstruct chunks of the spectrum by sampling many local bases. In solid-state devices, engineered edges and quantum simulators let you compare the real edge spectrum to the entanglement one computed from the bulk wave function, closing the loop. Even when a full spectrum is out of reach, proxies abound. Tomography of a small region's reduced state, learning-based reconstructions from shadow data, or spectroscopy of an entanglement Hamiltonian, the effective operator whose Boltzmann-like weights generate the spectrum, approximated along a cut in systems where theory predicts it mirrors a physical edge. There are cautions, and they make your use of the tool sharper. The spectrum depends on how you cut: real space, momentum space, or internal partitions. And some cuts are better matched to the relevant edge theory than others. Finite systems add finite-size splittings, so you look for level patterns that stabilize as you scale up, not for a single golden number. Thermal states blur the picture because true entanglement mixes with classical uncertainty, in which case a different object, the negativity spectrum, does a better job isolating quantum correlations. Strong disorder or long-range interactions can warp the edge bulk echo, so cross-checks with transport or symmetry diagnostics remain essential. And crucially, the spectrum's secret code is meaningful only within a gapped phase. At critical points, the level crowding becomes scale-free, and you should read that crowding as a signature of criticality rather than misfile it as a topological cue. Used wisely, the fingerprint becomes a design tool. When computational searches propose a new quantum phase, the first thing practitioners do is cut the state and read the entanglement spectrum for the expected degeneracy sequence. When engineers pattern heterostructures seeking protected channels, they simulate the target stack and confirm the right entanglement flow before committing to growth. When quantum devices drift under fabrication noise, monitoring the entanglement spectrum across the array can diagnose whether a lost feature is a mere local defect or a phase slip that destroys protection system-wide. The conceptual payoff you carry forward is subtle but empowering. The identity of a phase is not only about what excitations exist in the bulk, it is also about how information is shared across boundaries. And the entanglement spectrum is a direct audit of that sharing. It takes the most quantum part of a state, the pattern of non-classical correlations, and turns it into a readable barcode whose broad features do not care about microscopic clutter, but do care about symmetry, topology, and the presence or absence of an energy gap. Close gently with this. When you study matter by sawing it in half conceptually and listening to what the halves still know about each other, you discover that order lives as much in relationships as in local values, and the entanglement spectrum is the stethoscope for that hidden circulation. Place it on the boundary, hear the phase's heartbeat, and learn to trust that a clean, low-lying pattern is not decoration but diagnosis, a quiet signature that tells you which world you're in long before the ordinary senses can catch up. Area law versus volume law, entanglement. You expect more system to mean more quantum correlation. So here's a sharper way to listen to complex many-body states. Cut a piece of your system in your mind. Ask how much non-classical information it shares with the rest, and notice that in many of the most stable phases that shared information scales, not with how much stuff you kept, but with the size of the boundary you cut. That is the area law. While in highly excited, chaos-leaning states, it swells with the full size of the piece, a volume law. Begin with the calm regime where ground states of local, gapped Hamiltonians live, interactions are short-ranged, correlations decay within a finite length, and when you slice the system, only degrees of freedom straddling the cut can stay strongly entangled, so the entanglement cost is proportional to the boundary you created. Length in one dimension, surface in two, and so on, regardless of how thick the region is. This boundary budget is not a hand-waving slogan, but a consequence of locality and finite correlation length, reflected in rigorous bounds that limit how quickly information can spread. And in countless numerical studies showing that ground states of ordinary magnets, insulators, and superfluids quietly obey area-like scaling. There are refined accents inside this calm, near quantum critical points where correlations stretch across the system. The area law often picks up a gentle universal correction, typically a slow, logarithmic growth in one dimension that encodes the theory of the critical point. In topologically ordered phases, The area term is followed by a small but telling constant subtraction, a topological entanglement piece that does not care about the region's shape and whispers that the ground state carries long-range organizational memory invisible to any local snapshot. Now pivot to the noisy regime where the system is hot, highly excited, or driven into scrambles. Almost any state drawn at random, any thermal eigenstate at finite energy density, and many out-of-equilibrium states after long chaotic evolution display a volume law. The entanglement between a region and the rest grows in proportion to the number of degrees of freedom you kept, as if the cut exposed threads running through the entire bulk, not just the boundary. This is the operational content of why thermal states look classical in the parts you hold. The reduced state of a small region resembles a thermal ensemble because the rest of the system acts as a heat bath, and the entanglement needed to support that mimicry scales with volume, consistent with the eigenstate thermalization mindset, where individual energy eigenstates already encode thermal behavior locally. Dynamics paint the contrast vividly. Prepare a low entanglement product state and perform a global quench in a non-integrable many-body system. Entanglement grows linearly in time, as if bounded by a light cone velocity, quickly crossing into volume law territory and saturating at values set by thermodynamic entropy. Prepare the same quench in an integrable model, and you see a slower, structured growth where stable quasi-particles carry correlations in pairs, delaying saturation. Sprinkle strong quench disorder to create a many-body localized phase, and the surprise is that even highly excited eigenstates obey area law entanglement, a sign that local integrals of motion keep information from fully spreading, and out-of-equilibrium growth becomes painfully slow, logarithmic in time, so that the volume law never fully arrives. Experiments have moved this from blackboard to bench. Trapped ions in Rydberg atom arrays have measured Rényi entropies via interference of two copies and mapped the crossover from area-leaning to volume-leaning growth after quenches. Superconducting qubit processors and neutral atom platforms have used randomized measurements to estimate entanglement entropies of subsystems, while dialing between clean, chaotic, and monitored dynamics. Even circuits with intermittent measurements show a stark measurement-induced transition. Frequent local readout collapses correlations fast enough to enforce an area law, while infrequent measurements let unitary scrambling build a volume law, with a sharp threshold between them that can be tuned by the measurement rate. These patterns are not just taxonomy, they decide what you can do. Area law ground states admit compact classical descriptions. You can compress them into efficient variational forms that store only boundary-sized information. So simulation, optimization, and state preparation remain tractable. Volume law states resist such compression because the information crosses the bulk, so simulating their full quantum structure classically explodes in cost, which is why quantum advantage experiments deliberately steer hardware into regimes where entanglement grows volumetrically. The same logic guides error correction and device design. To keep a quantum memory quiet, you want entanglement that is structured and local, area-like, so noise can be detected and confined. To build processors that explore classically hard dynamics, you want controllable routes to volume law growth without losing readout. There are practical smell tests you can apply without heavy math. If doubling a 1D chain while keeping the cut in the middle barely nudges your measured Rényi entropy, you are in area law territory. If it jumps in step with length, you've hit volume law. If your system shows an almost constant offset across shapes that share the same boundary, you may be seeing the topological constant. If adding weak measurements suddenly flattens an otherwise rising entropy curve, you've crossed the monitored transition. And if strong static disorder makes high-energy eigenstates look modest in entanglement, you may be in a localized regime. There are also limits worth respecting. Real laboratories access proxies, second-order entropies, mutual informations, tomographic shadows, that approximate but do not equal the full entanglement entropy. So claims about scaling must be buttressed by finite-sized checks and cross-probes. Long-range interactions blur the boundary picture and can turn area laws into faster growths because distant parts talk directly, and open systems with uncontrolled baths can fake reduced entanglement by simply destroying coherence. A different mechanism from the gentle, information-selective pruning achieved by designed measurements. Carry the philosophical shift with you. How much is entangled is not a single knob, but a scaling law that reveals what kind of organization a state sustains, boundary-tethered correlations that signal locality and stability versus bulk-filling ties that signal thermalization or designed complexity and learning to read that. Scaling gives you both a diagnosis and a steering wheel. And close softly with the habit that will make the rest of this series clearer. Whenever you face a new quantum phase, a quench protocol, or a circuit design, don't just ask, how big is the entropy? And ask, how does it grow with size and time? And what does that say about the routes information takes here? Because the difference between area and volume is the difference between a world where entanglement outlines the perimeter and a world where it floods the interior. And that difference tells you, at a glance, whether you're looking at a state you can compress and control, or an ocean you must sail with quantum hardware. Tensor networks visualizing the invisible. You've stared at wave functions as if they were fog, everywhere at once, impossible to grasp. So here's a way to make the invisible legible. Redraw the state as a network of small, connected blocks and let wires between them stand for how much the parts talk. Then watch how questions about an entire quantum many-body system become questions about paths through that picture. Start gently by imagining a row of boxes, one per site in a chain, each box encoding how that site correlates with its neighbors, and thin wires between boxes carrying a limited set of possibilities. The thinner the wire, the fewer possibilities, the easier the state is to hold in your head and on your computer. That is the essence of a matrix product state. The workhorse representation behind modern algorithms that find ground states of long chains. Instead of storing an impossible encyclopedia of amplitudes, you store a necklace of small dictionaries and only ever read the entries you need. A strategy that owes its power to the simple fact that many low-energy states in nature are structured rather than random. This picture scales and bends to match the physics you're asking about. Draw a sheet of boxes for a two-dimensional material and link each site to its four neighbors, and you meet projected, entangled pair states, a natural habitat for models of magnets and superconductors on lattices. Stack boxes layer by layer in a branching pattern that coarsens as it climbs, and you arrive at a multi-scale network that doesn't just describe a state but displays how features at small distances are distilled into features at large distances, a kind of visual renormalization, where disentanglers peel away short-range quantum ties before you zoom out, and suddenly long-range order or scale invariance stops being a slogan and becomes a pattern your eyes can trace. What makes these diagrams more than art is that every line you draw corresponds to a concrete summation you can perform. Every crossing obeys rules you can automate, and the cost of answering a question like, what is the energy? Or what is the correlation between these points, is governed by how many wires you have to cut and reconnect, not by the full size of the system. That is why algorithms with names you may have heard, density matrix renormalization, imaginary time evolution, variational optimization, flow so naturally in this language. Each is just a systematic way to reshape a few boxes, restitch a few wires, and measure how the picture improves. Tuning the thickness of the internal wires, the bond dimension becomes your principal knob. At small values, the network stores only simple correlations and runs blazing fast. At larger values, it captures richer patterns at a higher cost. And this single knob lets you watch when a material's behavior genuinely requires long-range quantum memory, because the error plummets until a certain bond dimension and then refuses to fall further unless you pay for more wires. In practice, you use this both as microscope and meter. As microscope, because the network's shape, chain, sheet, tree, forces you to choose a hypothesis about which connections matter, and as meter, because the chosen shape tells you where an approximation will bend or break. This visual discipline pays off across fields you might not expect. In quantum chemistry, where electrons spread across orbitals with delicate entanglement, chain-like networks reorder those orbitals to make near neighbors in the network mirror strong correlations in the molecule, turning intractable bond-breaking problems into tractable optimizations and exposing which orbitals genuinely talk. In error correction, The decoding of planar codes becomes a network contraction problem, where the most likely pattern of errors corresponds to the dominant path through a web. So the threshold of the code maps to a transition in a statistical model you can analyze with these tools. In quantum hardware verification, the entire circuit is itself a network whose wires carry small indices whenever gates are local and depth is moderate. So you can simulate, compress, and compare measured outcome distributions to predictions far beyond what naive tables would allow, flagging crosstalk or miscalibrations when the network's contractions don't match the lab's. In quantum simulation, time evolving a calm state after a gentle quench is no longer a mystery of exponential blow-up, but a controlled growth of bonds you can track. And when the bonds begin to thicken linearly in time, you know you're moving from easy-to-describe dynamics into chaos that demands either more wires or a different approach. You can even bring experiments directly into the network world. Cold atom snapshots of many body configurations, taken over and over, can be fed into learning loops that fit a small bond network whose observables match the data, giving you a compressed, manipulable surrogate for the real state, while randomized measurements in trapped ion or superconducting qubit arrays provide just enough shadow information to fit local tensors without reconstructing the entire density matrix. The power of the picture grows when you impose symmetries at the level of each box. Charge, spin, lattice rotations, because you can block the wires so they carry labels for conserved quantities, which prunes impossible paths before you ever compute them, and turns respect the symmetry from a checklist item into a structural constraint that guarantees eigenvalues sit in the right sectors. And when you step to finite temperatures or open systems, the language stretches again. You represent operators as networks too. Evolve them, and compute expectation values by contracting two mirrored webs. So dissipation and noise become objects in the same diagrammatic space as states and Hamiltonians. The interpretability you gain isn't just computational, it's conceptual. Local observables depend only on a narrow causal cone through the web, so you can literally trace which parts of the network, and therefore which length scales and which neighbors, matter for a given measurement. And when you edit the boxes in that cone, you can see precisely how a local defect or gate propagates its influence. With multiscale networks, that cone broadens as you climb layers, a visual reason why certain perturbations change universal properties while others wash out. And in holographic toy models, the geometry of the network mirrors the geometry of an emergent space, offering a playground where deep conjectures about gravity and entanglement are translated into the movement of wires and the growth of minimal cuts. There are honest limits, and they are as educational as the successes. When a state's entanglement swells with volume rather than boundary, the wires you need multiply rapidly and your efficient picture strains, telling you've entered regimes, strong chaos, long-time dynamics, or highly excited eigenstates, where you either must change the network's topology, sprinkle in adaptive shortcuts, or hand the baton to quantum hardware. Long-range interactions demand cross-bracing that a simple grid of wires will not capture without extra scaffolding, and certain fractal or glassy structures hide correlations that defy tidy locality and punish over-eager assumptions about which boxes should connect. Even so, the network mindset gives you constructive workarounds. You can graft tree branches onto grids to catch hierarchical structure, couple neural elements to tensors so patterns the network struggles with get absorbed by flexible, trainable maps, or tile the plane with different patch shapes that align with a material's real space motifs. And when you must go hybrid, the picture remains your guide. Use a modest network to pre-process and compress a problem instance. Send the hard, entanglement-heavy core to a quantum processor, then pull the results back and stitch them into the classical web for interpretation. Most importantly for your day-to-day thinking, tensor networks teach you to separate mystery from mechanism. If a calculation refuses to converge until you crank the bond dimension, that's a signal about the physics, not just a numerical headache. If an observable depends only on a slender cone, you do not need to fear the full state's complexity to understand that measurement. If two phases look similar in two-point correlations but demand different network shapes to fit cleanly, you've learned that their organization of information differs in kind. and you can design probes to expose that difference directly. Close with a quiet shift in perspective. What once felt like a featureless fog becomes an engineered city map. Streets for short-range ties, avenues for longer-range structure, highways across scales, where computing is walking the shortest routes, and understanding is learning why certain blocks connect at all. With that map in your hands, visualizing the invisible stops being a metaphor and becomes a method, one that lets you draw, compress, and interrogate quantum matter without drowning in its amplitudes, so that you can move from awe to agency, choosing where to add detail, where to ignore it, and how to turn a sprawling, many-body story into a picture you can read, improve, and use. Virtual particles, what the metaphor gets wrong. You've seen the cartoons, little messenger balls pinging between charges, particles bubbling out of nothing and popping back before anyone notices. The imagery is vivid, but if you want a clear head, start by retiring the metaphor and learning what's really doing the work. Because virtual particles are not tiny actors that live brief lives. They're bookkeeping devices inside a calculation, terms in an expansion that help you solve for how fields influence one another, and confusing them with real detectable quanta leads you into traps that good physics never falls into. Begin with the actual task a theorist faces, predicting what your detector will register long before and long after an interaction. And the honest language is fields plus probability amplitudes. You set up incoming waves. You let them interact according to rules fixed by symmetries and couplings, and you compute the amplitude for each allowed history. Feynman diagrams are a clever shorthand for pieces of that amplitude, and the lines you're tempted to call virtual particles are just internal connections in this bookkeeping, integrations over all possible intermediate momenta that satisfy the overall constraints. No detector can click on an internal line, no camera can catch it mid-flight, and energy momentum conservation is not violated for a short time, while these lines borrow energy. That popular slogan is precisely what the metaphor gets wrong, because conservation holds exactly at every vertex and for the entire process, while the off-shell nature of an internal line means only that the intermediate variables you integrate over don't satisfy the real particle dispersion relation. If you've been told that forces are literally carried by exchanged particles, clean this up too. Real quanta carrying momentum show up when something radiates. An antenna broadcasts. An atom emits light, whereas the static pull between two charges is better viewed as the response of a field that fills space. And although you can rewrite that static influence as a sum over virtual exchanges in a particular formalism, nothing in your lab will ever count those internal lines the way it counts photons from a lamp. Feynman's pictures are powerful because they encode the algebra of propagators and couplings, not because they depict a frame-by-frame movie of little bullets. This distinction matters when you hear about vacuum borrowing energy to make a particle-antiparticle pair. What's real are fluctuations of fields and the way interactions modify measurable quantities, energy levels in atoms, magnetic moments of electrons, not a rain of short-lived particles you could bottle if only you were quick enough. Even emblematic effects often used to sell the metaphor, like small shifts in atomic spectra, are best understood as how the electromagnetic field's correlations are altered by interactions and boundaries, not as swarms of popping pairs pushing plates or tickling electrons. When is it sensible to talk about particles at all? When your system supports long-lived, on-shell excitations that travel to your detector and deposit energy in discrete clicks. Photons in a photodiode, electrons in a calorimeter, phonons in a crystal resonator, and the theory signals those realities through sharp poles in the relevant response functions. Internal lines don't correspond to those poles. They're parts of an integral whose final summed result is the only thing you can test. This is also why what exchanged particle did a static magnet use has no single experiment-independent answer. In one gauge, the diagram may look like a chain of exchanges. In another, you might trade that picture for a different field decomposition. And all gauges give the same measurable predictions precisely because the internal story isn't observable. Keep this in view when you read about loops and virtual corrections. Those loops stand for how interactions renormalize parameters, the charge you infer from far away versus up close, the mass you deduce from motion in a field. So yes, loops change numbers you can measure, but the only honest cause is the field interacts with itself and with others, not ghost particles nudged it while no one was looking. The same sobriety clarifies energy-time uncertainty, another breeding ground for myths. That relation tells you how sharply you can define energy in a process that lasts a finite time, not a legal loophole that lets nature break conservation so long as it repays the debt quickly. If a process outputs more energy than went in, you misdescribed your system. Full stop. Set against the excesses of the metaphor, there are constructive uses of the language you can keep. In perturbative regimes, saying mediated by a virtual photon is shorthand for governed by the electromagnetic propagator, and loop of virtual leptons means higher order terms where charged fields alter the propagator. Used that way, anchored to calculations, not to mental movies, the phrases remind you which pieces of the math are doing the heavy lifting. But notice the boundary. When the physics is strongly coupled, the tidy expansion into diagrams fails, and non-perturbative methods take over. Lattice simulations, bootstrap constraints, effective theories that never mention a virtual particle at all. Yet predictions continue without any need for the metaphor. Experiments keep you honest about all this, because detectors are the final court. They count on shell quanta, they resolve spectral lines, they map cross-sections as functions of incoming energy and angle, and none of those observables ever depends on how you narrated the internal lines. Two analysts, using different gauges or reorganized expansions, will get the same numbers if they calculate correctly, which is the formal way of saying the virtual story is not a piece of the world, but a human-chosen scaffold. This clearer picture even helps you think about neighboring ideas more cleanly. Static fields can be described as coherent states of many real quanta, but that statement is a choice of description, not an extra population you could suddenly release. Radiation reaction and damping are about how a source couples to the continuum of field modes, not a tug of war with a cloud of evanescent messengers. And when a heuristic threatens to smuggle in perpetual motion, could we harvest the energy of virtual pairs? You now have the answer ready. There's no reservoir there, only correlations that show up when you interact with the field, and every device you might build ends up paying as much as it harvests once you account for the full system. So what should you say instead of virtual particles pop in and out? Say that fields permeate space, that interactions are encoded in propagators, that perturbation theory organizes contributions by powers of coupling, and that internal lines are integration variables whose sum predicts real, testable outcomes. And when you want an image, use one that keeps cause and effect straight. Think of Feynman diagrams as architectural blueprints, lines and vertices specifying how pieces fit. Useful for building, meaningless as literal furniture. We can end gently with the payoff of letting go of the metaphor. You gain a steadier intuition, one that doesn't need to wink at conservation or imagine invisible crowds, and you learn to ask better questions. What are the symmetries that fix the form of the interaction? What scales set which terms matter? What observables are sensitive to which parts of the calculation? With that discipline, virtual particles shrink back to the helpful scribbles they always were, and the world becomes simpler, not stranger. Detectors click for real quanta, fields carry influence according to rules we can write and test, and the math that leads from one to the other is the story worth telling. Radiative corrections, the self-energy story. You think a particle just is what it is, an electron with a fixed mass and charge, a tidy entry in a handbook, so here is the gentler, truer story that careful measurements keep repeating. Once a field is allowed to interact with itself and with its companions, the very act of existing in that sea adds a self-energy, a subtle back-action that shifts the numbers you would otherwise call intrinsic. And what we name radiative corrections is the disciplined way of reckoning with that shift. So predictions match what your detectors actually see. Begin with the picture that doesn't lie to instruments. No charged particle moves through a silent void. It constantly couples to the electromagnetic field and to other charged fields. And that coupling means it drags around a cloud of influence. Nearby modes briefly stir and then settle. and your attempt to measure the particle alone is always, in practice, a measurement of the particle plus its dressing. Now, when you translate this into calculations, the neat but incomplete answer you get at first order is improved by terms that represent those stirrings. And some of those terms try to push your parameters to infinity if you take the continuum literally. Radiative corrections are not a license to shrug and love infinities. They are a bookkeeping method that insists you separate what is definition from what is prediction. You define a few physical inputs at a chosen scale, say, the mass you infer from kinematics and the charge you measure in a low-energy scattering. And you adjust the bare symbols in your equations so that, after the cloud's contribution is included, the outputs match those inputs. After that, every other quantity you compute becomes a bona fide prediction tied to the same definitions. And the proof you have done this properly is that different renormalization schemes, all making the same set of physical identifications, yield the same answers for observables. The phrase self-energy earns its name most transparently for the electron. Classically, you could already sense trouble by asking how much energy sits in the electron's own electric field as you squeeze its radius towards zero. And quantum field theory refines that worry into a controlled calculation that shows how the electron's mass and charge you plug into an equation are not what you get out unless you include the self-fields effect. This is not borrowing energy for a short time. It is a permanent shift in the relation between parameters and measurements that stabilizes once you choose your renormalization point. The beauty is that the same machinery that cures the mass shift also predicts delicate, testable distortions and other properties. The electron's magnetic moment is not exactly 2 in the natural units, favored by theorists but slightly larger by a calculable margin because its self-interaction makes the magnetic response bloom beyond the simple picture. And the Lamb shift, the tiny reordering of hydrogens, energy levels that stunned mid-century, spectroscopy, arises because the electron's coupling to the field reshapes the effective potential. It feels near the nucleus. If you listen for pattern rather than detail, you hear the same refrain. Radiative corrections take idealized parameters and, through the medium of the vacuum's response and a particle's own field, deliver the corrected values that atoms and beams actually reveal. There is a second moral embedded here that will serve you well. Self-energy does not only shift a number, it also introduces scale into a world that would otherwise be mute about distance. When you probe at short range or high energy, the cloud dressing the particle is less able to screen or smear, and effective couplings change in a predictable way. This is running, and the equations that describe how the numbers evolve with scale form the renormalization group. Think of it as learning. You must specify the temperature when you talk about ice and water. The substance is the same, but its response depends on the conditions. And once you say the temperature out loud, predictions stop contradicting each other. Equally important is the division of labor between self-energy and cousins like vacuum polarization. Both live under the umbrella of radiative corrections. But the first tells you how a single line in your mental picture is dressed, while the second tells you how the medium between sources becomes polarizable. Together they change masses, charges, scattering probabilities, and spectra. But keeping the roles distinct clarifies where each effect shows up in data. The mathematics behind this story can look forbidding: integrals, subtractions, and careful limits. But the conceptual guardrails are simple enough to carry. Conservation laws hold at every step. Symmetries tie parameters together so that charge is renormalized in lockstep with the vertex that couples matter to the field. And gauge invariance guarantees that unphysical artifacts of your choice of description cancel from the final answers. You may have heard renormalization mocked as sweeping infinities under the rug. Yet the modern view flips that completely. Interactions at arbitrarily small distances are not things we must know to make predictions at accessible scales. Instead, we classify the few ways short distance ignorance can leak into long-distance physics and show that with a handful of measured inputs everything else is fixed. This is why effective field theory feels both humble and powerful, letting you compute reliably up to a cutoff that marks where new phenomena must be resolved explicitly. The laboratory keeps this from drifting into philosophy by pinning numbers with brutal precision. The anomalous magnetic moment of the electron matches theory to dizzying digits once self-energy and its companions are included. The muon's magnetic moment tests the same ideas with heavier loops and has become a frontier for hints of new charge fields in the dressing. And the Lamb shift continues to calibrate our treatment of radiative corrections in bound states, where fields are strong and distances are small. Even outside high-energy physics, the same self-energy logic gives you intuition. In metals, an electron's interaction with its environment produces a self-energy that shifts its dispersion and lifetime. And while the microactors differ from the vacuum story, lattice vibrations and other electrons dominate, the operational lesson is identical. The entity you move through a medium is dressed, and you must measure or compute the dressing to predict transport and spectra. There are clean limits to respect so you don't overgeneralize. Radiative corrections do not mint energy you can harvest. They do not grant exceptions to conservation in brief windows, and they do not force every number to drift wildly with scale. Rather, they organize small but crucial departures from the simplest approximation into a hierarchy you can cut off at the needed accuracy. Sometimes the hierarchy fails. Strong coupling can make the first correction as big as the leading term. But even that failure is informative, telling you to switch methods rather than to abandon the idea that parameters are dressed. The softest and most practical payoff is a change in how you read mass and charge on a data sheet. These are not platonic labels carved into particles once and for all. They are calibrated descriptors of how a system responds when probed in a specified way, at a specified scale, after the self-energy is properly included. Accept that, and several puzzles melt. Why different communities quote slightly different values for the fine structure constant. Why the definition of a quark mass depends on convention, even though hadron masses do not. Why some quantities are astonishingly stable under radiative corrections while others drift faster. It also gives you a work ethic for precision. State your renormalization conditions clearly, compute to the required order with the right symmetries enforced, and compare to observables that are actually measured in the same regime. Close gently with the version of the story that fits on a note card without losing the thread. A particle in a world of interactions is never naked. It wears a cloud of its own making, and radiative corrections are the tailoring that lets theory cut that suit to the shape experiment sees. When you honor that, masses and moments and couplings stop being abstract symbols and become numbers with context, and the supposed weirdness of self-energy turns into a simple, testable message. Everything influences itself a little, even in perfect emptiness. And accounting for that influence is what turns a sketch of nature into a calculation you can trust. Renormalization, taming infinities, keeping physics. You hear infinity and think catastrophe, so let's start with the calmer truth. Renormalization is not a trick to hide divergences, but a method for telling nature which questions you're really asking, trimming away details you can't see while keeping every prediction that you can. And the reason it works is that physics at long distances seldom cares about every wrinkle at the shortest ones. Imagine building a map. If you're driving across a country, you don't draw every pebble. You keep highways and towns. And somewhere a cartographer decides the scale, the cutoff, beyond which detail is averaged. Quantum fields force the same honesty because naive calculations ask particles to interact at arbitrarily short separations, and the resulting integrals explode. So the first adult step is to regulate. Impose a yardstick, whether a hard momentum limit, a lattice spacing, or a change of dimension, and then measure a few anchor quantities in the real world at a declared scale. A mass from a resonance, a coupling from a scattering rate, a field strength from a magnetic moment. Those measurements define what the symbols in your equations mean for your chosen resolution, and the infinities are revealed as artifacts of demanding knowledge beyond that resolution. Renormalization then does two things at once. It reshuffles the bare parameters, so the regulated theory reproduces your inputs exactly, and it tells you how predictions for other processes change when you move the yardstick, how the couplings run with scale, and why a number printed on a data sheet comes with an implicit context, like a temperature printed beside a material property. The Wilsonian picture makes the logic visual. You integrate out short-distance jitters in thin shells, step by step, and watch your rulebook flow in a small space of all allowed interactions, with some terms swelling in importance as you zoom out, relevant, some fading, irrelevant, and a rare few sitting on the knife edge, marginal. That flow explains universality, the relief that magnets, fluids, and mixtures share exponents not because their atoms match, but because, under coarse graining, they fall toward the same fixed point grammar, and it explains predictivity. Although infinitely many interactions are allowed by symmetry, only a handful survive the zoom out as serious players. So, a finite number of measured inputs pins down a vast number of outputs. The field theory version reads differently but means the same. You pick renormalization conditions to define parameters, add counterterms whose sole job is to keep those definitions stable as the cutoff moves, and compute beta functions that report how each coupling drifts when you change the probe scale. Clean examples keep your intuition anchored. In the low-energy theory of weak decays, a single 4-fermion interaction predicts rates beautifully until your experiments approach energies where the underlying heavy carriers matter, at which point, matching to a more complete theory, hands the baton upward without contradiction. In quantum electrodynamics, the observed charge grows gently with resolution because vacuum polarization screens more efficiently at long distances than at short. So high-energy scattering sees a slightly stronger interaction than atomic spectroscopy does. In the strong interaction, the opposite happens. The coupling weakens at short distances, so quarks behave almost free inside a tightly focused probe. A feature that turned what looked like nonsense in early integrals into a cornerstone of our understanding. None of this is sweeping infinities under the rug. The rug is your declared scale, the sweeping is an honest average, and the proof of honesty is that different regulators and different schemes all agree on observables once you specify how your parameters were defined. The method earns its keep precisely where naive pictures fail. It quantifies how sensitive a prediction is to short-distance ignorance. It ranks operators by how loudly they speak at your scale. And it tells you when a model has real leverage, few relevant couplings, and when it is merely a catalogue awaiting more data. It also brings order to conversation across communities. Condensed matter physicists speak of blocking spins and extracting fixed points. Particle physicists of beta functions and running couplings. Quantum chemists of active spaces and effective Hamiltonians. Yet the shared ethic is to keep what matters for a chosen window and fold the rest into renormalized parameters. The practical workflow is less mystical than its reputation. Regularize. Define your inputs at a reference scale. Compute corrections with symmetries, enforcing the allowable forms. Evolve parameters with the renormalization group to the scale of the measurement. And compare to data, adjusting only the few inputs you promise to adjust. When you change the question, probing at a different energy, resolving new states, or tightening uncertainties, you redo the last steps with the same compact rulebook. Renormalization also clarifies debates that otherwise churn endlessly. What is the mass of a quark? Becomes which definition do you mean at which scale? And once you pick a convention, the translation between schemes is a matter of running and matching, not metaphysics. Is this theory natural? Becomes, do small inputs stay small as I run? A quantitative worry about sensitivity to short-distance physics that guides search strategies rather than a veto on ideas, even anomalies, places where a symmetry of the equations fails after regularization. Learn their meaning here. A good regulator preserves the symmetries that must survive in observables, and when one cannot be preserved, the residual, scheme-independent violation is a measurable feature, not a mistake. Yes, there are edges. At strong coupling, the first terms in a perturbative flow may not dominate, so you switch to non-perturbative tools, lattices, bootstrap constraints, dualities that implement the same renormalization ethic without expansions. Near certain fixed points, small, irrelevant operators can steer physics if your experiment is exquisitely sensitive. So care with error bars and subleading corrections is part of the craft. And beyond some frontier of energy or precision, new degrees of freedom must be made explicit, the very point where an effective theory gracefully hands you upward rather than breaking. But within those edges, the payoff is enormous. Infinities are tamed into scale dependence. Fuzziness is repackaged into a few measured constants. and the prediction factory runs, producing cross-sections that match collider counts, spectra that match atomic clocks, critical exponents that match neutron scattering, and transport laws that match chips under load. If you keep one habit from this, let it be to say out loud the scale and scheme attached to any parameter, then to ask how it runs and what counts as relevant at the scale you care about, because that habit turns renormalization from a word people whisper into the method by which we keep physics finite, falsifiable, and transferable across problems, while acknowledging that our maps always have a resolution, and we can close softly with a reframing that frees your intuition. The world does not demand that you know every short distance detail before you can predict what happens in your lab. It lets you coarse grain, define, and flow. And renormalization is the discipline that makes that license precise, turning infinities from threats into signposts that point to a better language for the same measurable reality. Lamb shift, vacuum nudges atomic levels. You learn in school that an atom's energy levels are neat rungs on a ladder, set once and for all by the Coulomb pull between an electron and a nucleus. So let's open the door where that tidy picture bends. Even in perfect darkness, the electromagnetic field never quite sits still, and that restless backdrop nudges the rungs by tiny, measurable amounts, the Lamb shift, turning what seemed like a crisp degeneracy into a split you can hear with the right kind of radio. The story begins in 1947 with a deceptively modest experiment. Willis Lamb and Robert Rutherford coaxed hydrogen atoms into a long-lived excited state and then used microwaves to make them hop to a neighboring state that Dirac's elegant theory said should be at exactly the same energy. Instead of silence, the atoms responded at a slightly offset frequency, betraying a small energy difference between two levels, one with orbital motion that keeps the electron mostly away from the nucleus, and one with a wave function that spends real time at the very center. That offset, only a part in 100 million of the atom's total scale, was big enough to be unmistakable, yet small enough to expose a missing ingredient. The electron is not an isolated bead circling a point charge. It is a quantum field coupled to another quantum field, and the constant give and take between them subtly reshapes the landscape the electron feels. The cleaner explanation is wonderfully concrete if you keep jargon at a distance. An electron in an atom does not simply sit in a static potential. It keeps coupling to the electromagnetic field's own modes. And those modes, in virtue of being quantized, push back. Two effects dominate this push. First, the electron's self-energy, the way its own field alters its motion when you allow the possibility of emitting and reabsorbing very soft light. Second, the polarization of the vacuum near the nucleus, which slightly screens the nuclear pull. Neither effect showers the atom with real photons, and neither requires you to imagine energy being borrowed. Yet together they shift the balance by a small, calculable amount that depends on how the electron's probability cloud overlaps the nucleus. This dependence is the fingerprint you can hold in your head. States with zero orbital angular momentum have a non-zero chance of the electron sitting right at the origin, so they feel the dressing more strongly than their partners with 1 unit of orbital motion, whose donut-shaped cloud avoids the center. That is why the specific pair Lamb measured, the two levels that Dirac had pegged as degenerate, stubbornly split. The one that pokes the nucleus more is lifted differently than the one that skims around it. The first theoretical foothold arrived fast. Hans Bethe, working with a back-of-the-envelope tenacity on a long train ride, showed how to compute the leading piece of the effect with simple, non-relativistic tools and a sensible high-frequency cutoff that stands in for the fact you can't ask nature to respond to wavelengths far shorter than the theory's reach. More refined treatments soon followed, and the infant framework of quantum electrodynamics grew into a precision engine. Calculate the atom's response, including the self-feedback from the field. Define what you mean by mass and charge at a reference scale, and watch the predicted splitting land exactly where the measured one sits. What kept the Lamb shift important is its role as a recurring truth, rather than a one-off curiosity. Modern spectroscopy measures it not only in ordinary hydrogen, but also in deuterium and in helium ions, checking how the shift scales with nuclear charge and with the subtle differences in wave function overlap. In muonic hydrogen, where a muon orbits 200 times closer to the proton than an electron would. The same physics is magnified dramatically. The muon samples the nucleus's interior as well as the vacuums, push, and the resulting lamb-like splittings have been used to extract the proton's size with exquisite sensitivity, fueling a lively debate when early measurements disagreed with other determinations. You can flip the perspective and use the shift as a tool. Knowing how the vacuum and the nucleus together reshape levels lets you isolate nuclear structure effects. So atomic clocks and simple atoms become laboratories for the proton's charge distribution and for tiny possible drifts in the constants of nature. And you can manipulate the shift on purpose. Place an atom near a reflective surface or in a cavity that suppresses or enhances certain field modes, and you change the self-interaction in a controlled way. The same logic behind the Purcell effect that boosts emission rates also adjusts level positions by altering what fluctuations are available, a reminder that vacuum is not a uniform backdrop, but a set of allowed field patterns that your apparatus can edit. Distinguishing the Lamb shift from its cousins helps you think cleanly. The Axe-Stark shift comes from real, applied light that dresses the atom in a controllable way, while the Lamb shift is the baseline readjustment present even when the lab is dark. Hyperfine splittings trace magnetism tied to the nucleus's spin, while the Lamb shift is there whether the nucleus spins or not. Finite nuclear size contributes too, but in simple hydrogen, the vacuum's role is big enough to stand alone, and in heavy nuclei, the balance tips subtly as the electron cloud piles up more near the core. The progress of measurement technique turns all this into a story with numbers, not adjectives. Laser-cooled atoms narrow Doppler blur, frequency combs stitch optical and microwave time together, and modern fountains and ion traps pin transitions down to parts in 1015 or better. So the Lamb shift isn't law, it's a calibration standard that theory has to meet. The philosophical payoff sits quietly in the background. We learned that an energy level is not only about a static potential, it is a property of a coupled system that includes a sea of quantum fluctuations, and that properties we were tempted to call intrinsic, like the spacing between rungs, carry a small tag that reads, defined in a world with this field content and this spectrum of allowed modes. None of this licenses sloppy talk about harvesting energy from the vacuum or detecting swarms of short-lived particles inside an atom. What is real are the tiny disciplined shifts that persist when you subtract every classical effect and that reappear across species, isotopes, and environments. And none of it undermines the simplicity you began with. Rather, it enriches it. Coulomb's ladder remains an excellent first draft, and the Lamb shift is the editorial margin note, written by a quantum field that refuses to be silent. End with the habit this teaches. When a prediction misses a precise measurement by a sliver, do not rush to add new entities. First ask how the ever-present field environment reshapes what the system by itself even means. The Lamb shift was the moment physics learned to ask that question systematically, and answering it turned empty space into a measurable participant, one that moves atomic lines by a whisper, yet anchors an entire theory to reality, when solid is just organized vibration. You think solid means stillness, a halt to motion, yet the steadier truth is softer and more beautiful. A solid is a choreography, not a freeze frame. Atoms or molecules hover around preferred places while ceaselessly vibrating. And what you call solidity is the reliability of those average positions and the organized ways the jitters cooperate. Begin with an image you can hold as you breathe. Each atom sits in a small valley of a shared landscape sculpted by its neighbors. And even at absolute calm, it can't rest at the exact bottom. Quantum rules give it a baseline tremble. So a crystal is a community of particles bobbing in unison around a repeating pattern, while a glass is a community that found a stable but irregular arrangement and vibrates around that. Because these vibrations are collective, not lonely. They come in modes that span the material. Some are long, low undulations where whole neighborhoods rise and fall together. You hear those as sound. Others are quicker, where adjacent sublattices move against each other. These show up in the infrared and tell you about internal structure. The stiffness you feel with your fingers is simply the cost of nudging those modes. Push on one face of a crystal, and you are slightly shifting a spectrum of vibrations, and the speed at which a tap echoes through steel or wood is set by how tightly the constituents tug on each other and how heavy they are. Heat in a clean insulator is nothing more mysterious than a crowd of these vibrational packets carrying energy from warm to cool. And the reason a perfect crystal can channel heat so well at low temperature is that the vibrations fly long distances before scattering, while defects, rough edges, and the random geometry of a glass knock them off course and turn a potential highway into a maze. Specific heat, the measure of how much energy you must pour in to lift the temperature, is a census of how many vibrational notes are available to be played. At ordinary warmth, almost all the notes are excited, and many solids demand roughly the same energy per atom, while deep in the cold only the longest, lowest notes participate, and the energy needed shrinks rapidly. This is why the gentlest cooling becomes harder, and why cryogenic engineers count vibrational modes as carefully as accountants count coins. Even expansion under heat, which sounds like a separate story, is written in this language. If the restoring forces were perfectly symmetric, a vibrating atom would spend as much time too close as too far, and the average spacing would not change, but real bonds are slightly anharmonic. The wall is steeper one way than the other, so a bigger wiggle biases the average outward, and the lattice grows. Materials that contract when warmed are the exception that prove the rule. Their internal geometry lets certain modes pull neighbors together as they excite, a design trick chemists now exploit to build composites with near-zero expansion for precision optics. At the other extreme of motion lies melting, which you might picture as breaking bonds. But a more predictive rule of thumb says, when the typical vibrational amplitude swells to a certain fraction of the spacing between sites, the lattice can no longer provide a stable reference and shear rigidity collapses. The organized dance slips into a flowing one. Look closely and you'll see why perfectly solid isn't a single category. Crystals break continuous translational symmetry. They choose a repeating pattern, and that choice gifts them long-lived shear modes and sharp peaks in diffraction. Glasses keep mechanical strength without long-range order, so they lack the tidy peaks and host an extra population of low-energy vibrations that neither race across the sample nor localize completely. A surplus many experiments here as a boson peak, a bump in the vibrational density that affects low-temperature thermal behavior and the way sound attenuates. Defects, vacancies, interstitials, dislocations are not mere blemishes, but new pockets in the vibrational landscape. Some trap localized modes, others scatter long waves, and still others, like dislocations, glide when certain modes are pushed, letting a crystal deform plastically at stresses far smaller than you'd expect if the whole lattice had to move as one. This vibrational view also reframes how solids talk to light and radiation. A gamma ray can be emitted without the source atom recoiling noticeably if the entire lattice shares the kick, which only works because a bulky solid can absorb momentum by gently exciting its lowest modes, a recoil-free process that made ultra-precise spectroscopy possible. Place the solid in a microcavity, and the allowed electromagnetic modes change, and with them, the rates at which lattice vibrations exchange energy with light, enabling devices where phonon lasers and optomechanical cooling turn mechanical motion into a controllable, near-quiet whisper. If you prefer design to description, the same picture hands you levers. To build a thermal barrier, you roughen and layer, so vibrations of different wavelengths see mismatched impedances and reflect. To spread heat rapidly, you align grains, polish interfaces, and purify so long wavelength modes can travel ballistically. To sculpt sound, you pattern resonant inclusions that open gaps in the vibrational spectrum, creating phononic crystals that block specific frequencies, much like electronic band gaps block electrons. At tiny scales, engineered beams and membranes turn single vibrational modes into sensors for mass, force, and acceleration so sensitive they can feel the landing of a single molecule, and the way those modes lose energy through surface friction, clamping loss, or conversion into other vibrations. Reads like a checklist of where the dance leaks into the room. Softness, too, is vibration reorganized. In powders and foams that jam, Rigidity appears not from an orderly lattice, but from a network of contacts that supports certain collective modes while killing others. So the line between solid-like and liquid-like becomes a statement about which vibrations survive across the sample. Even seemingly alien phenomena join the chorus when read this way. Negative refraction for sound, topologically protected edge waves in mechanical lattices, and metamaterials with programmable stiffness all arise by arranging masses and springs, atoms and bonds at one scale, beams and hinges at another, so that the permitted vibrations do your bidding. You need no equations to keep the through line. A solid is a pattern plus the allowed ways that pattern can wiggle. And every mechanical, thermal, and many optical properties are summaries of those wiggles. How many, how fast, how they scatter, how they couple. The humility this gives you is practical. When a measured property surprises you, ask first which vibrational modes you forgot. Was there an extra scattering channel? An interface that reflects? A low-energy band you inadvertently opened? A defect network that reroutes energy? And we can end softly with the reframing that steadies your intuition beyond the lab. Solidity is not the absence of motion, but motion held in agreement. It is the serenity of organized vibration, a quiet choir whose harmony gives you a place to stand, a tool to build with, and a language to design by. Once you learn to hear the score, the apparent stillness of a tabletop, a bridge, or a crystal becomes what it always was, music slow enough to touch.